when to do the specialization and knowing where to find the information about the closure. So we can close our parentheses and get back to our limitations to see how we solve them. The first one was when the block is not known syntactically. Let's say we have a function, return block, that takes ptr and returns the same block as usual, the one that assigns 42 to the dereferencement of ptr. If we look at the post condition of the specifications for that function, we see that the return value is a structure with the captured by value 0 field that is ptr, and an attribute that tells us what function it is. So we know all the information we need about the closure in the specifications of return block. Because we know all that, a function that were to call the block returned by return block could surely call the right function properly. That means give it the context and all that. And actually, it can, and it does. So we can see in the specifications of call return block that ptr will point to 42 in the post condition and must be valid in a precondition. Now the question is, what if we give block as an argument to apply? Well, in that case, we don't see the effects of block. So we have to solve that. This is the problem we have at the moment, the limitation. And well, to solve it, we try to use the information we have during pulses analysis. During pulses analysis, we know all the information about the block closure. We know what it captures and we know what function it is. And we even know the equivalent pseudocode we have. And if we look at the pseudocode, well, syntactically in it, we can see everything. So instantly, we could just try to reuse the solution we had before with the block inlining, code specialization, and context propagation, except that we just don't need the block inlining because we already have all the information at call sites in the memory model. So all we need to do is the code specialization and the context propagation. For the context propagation, it's straightforward. We said that the captured variables are stored as fields in the structure, so we just have to pass them for the context. And we just have to pass them in the order of the indices. Here there is only one, so it's quite easy. For the code specialization, well, we can do the same as we did before, give the right specialization information, that is f is the block 6 function, and replace the call to f by a call to the block 6 function, and give it the context it needs. And I said we can do the same because we're actually doing the same. This is the phase 0 happening right now. This is the phase 0 because in infer, what happens is that during pulses analysis, we will create the new callee, the copy that needs to be specialized. And because this is a new function, it will be pre-analyzed. So we benefit from the pre-analysis specialization on it. The phases 0, 1, 2, and 3 will apply to it before it is being analyzed by pulse again. So the two specializations work together. And like the pre-analysis specialization will go as deep as it needs to in the call stack, pulses specialization as well. Using that, we can now have the right specifications for the apply return block function. That is, ptr will point to 42 in the post condition and must be valid in a precondition. The next limitation we had is with disjuncts, if the block is assigned different values in different branches. So here we have a disjunct function that takes ptr as a parameter and a boolean. The boolean is a condition under which we will assign a value to block. If the condition is true, then the block is the same as usual. It will assign 42 to the dereferencement of ptr. If the condition is false, then the block does nothing. And after all those assignments, we'll give block as an argument to apply. If we look at the specifications for that function, they're quite long. Again, you don't have to read them. I will show you what's important, but they're quite long, maybe twice as long as we would expect. And that would be right, because in them, we have two preposts. One when the condition is false, one when the condition is true. The fact that we have two preposts is because in pulse, analyzing this code is equivalent to analyzing the code on the right, where all the code that was after the branches is moved inside the branches. Because in pulse, we don't try to join the preposts of each branches. We keep them separated. And if we look more in detail to what we have doing pulses analysis, well, we have a situation that looks a lot like the first limitation we had. Here we know all the information about the block when the condition is true, all the information about the block when the condition is false, and each of these blocks, known blocks, are given to apply separately. So it can just do the same specialization before. We don't have anything more to add to it. It works already. So now we will create the two specialized versions of apply. Apply specialized one that takes some context, and apply specialized two that doesn't take any context because block did not capture anything. And for the specialized calls, well, apply specialized one calls the right function, the block disjunct 3, and give it ptr for its context. And the apply specialized 2 calls the block disjunct 4 function and doesn't give anything because, again, it didn't capture anything. So now we can look back at our function after the specialization, and more importantly, at the specifications we have in the case the condition is true. We focus on this case because that's where the block does something. It assigns 42 to the dereferencement of PTR. And if we look at what we have in the specifications for this branch, we have the information in the post condition that PTR points to 42, and in the precondition that it must be valid. So it's solved. Now we are done with the two first limitations that were cases where the block is given directly as an argument. Now we have two more limitations where the block is not a direct argument. The first one, the block is stored in an object, and this object is what we will give as an argument. For that case, we will use the apply field function that takes an object and calls the block field of this object. If we look at the specifications for that function, they have two preposts, one for the object being nil, one for the object being not nil, and it ignores the effects of object block. We can read that out if you want to. There are two preposts, and in the case the object is not nil, the state of the memory in the pre and the post is the same. The only difference is the attribute we have on the block field of obj that says that it's a block that must be valid because we are trying to call it. And so we have the need specialization information that is set to true in those specifications. They're set to true because we were missing the information we are trying to tell the caller to give it to us. Now we can move on to a caller of that function, here blocking obj. In blocking obj, we'll assign the same block as usual to the obj.block. So the field block of obj assigns 42 to the dereferencement of PTR, and we give obj as an argument to apply field. If we look at the specifications for that function, while the pre and post condition are the same, there is no attribute on PTR, and we need specialization. And that seems quite weird because, well, surely the block's information is not coming from the outside, so we shouldn't need specialization. But as I explained earlier, if the caller fails to specialize the callee, then it will set that information to true as well to tell the caller to try to do the job and so on and so forth until someone does the job. But hey, no caller can do it because all the information is stored in blocking obj. We can see it here. Its obj.block is equal to a certain block. And even more so, when looking at the information we have doing pulses analysis, we know everything about obj.block. So clearly, there is no need for specialization. Well, no need for specializing blocking obj, but apply field needs to be. And we just failed to do it because that's a new case we haven't seen before. So we'll do the same as we did at the beginning and try to do it by hand to see what we need. If we were doing it by hand, we would inline the information we have about obj to see the block explicitly. This is not something we can write in CIL. This is just for the example. And if we were able to write it, surely we will be able to see the block that is being used and so do the specialization for apply field. And we will tell apply field that the obj.block function is the blocking obj function, and it will replace the call as it needs to. And that's where the key is. We need to be able to tell the function that the field block of obj is a certain function. If you remember, this is specialization information. What we had before for the specialization information was just a map from variable to block. So we were able to say that f is a certain function. What we'll have now is a map from variable to block and from variable to object. This way we can say that a parameter is a certain object, and objects will be maps from field to block and field to object. So now we can say that a field block of an object is a certain function. Allowing for the field to object association in the object representation allows for blocks to be stored as deep as we want to. So they can be the field of a field of a field of an object. Now that we have this new representation for the specialization information, instead of writing ob.block is a certain function, we can say obj is a certain object and its block field a certain function. That new specialization information will be accounted for by the phase 0 of the pre-analysis. And so when it sees a field being called, it will be replaced by the call to the right function. The phase 0 is updated, and also the specialization during pulse is updated to look in the memory to what we have in the objects that are being passed to find the blocks there. And passing the context of those blocks is quite easy. You just have to pass the field of the object. All right, so now we solved this case. We have the right specifications. In the post condition, we can see that PTR points to 42, and in the precondition, PTR must be valid. We now have the last case to solve, the one where the block is captured. For that, we have the captured block function that takes PTR as a parameter and defines two blocks, captured and capturing. Captured is the same block as usual, assigning 42 to the dereferencement of PTR, and capturing simply calls captured. And we give capturing as an argument to apply. If we look at the specifications for that function, we see that it says that it needs specialization, and we don't see the effects of captured. But it's surprising that it says that it needs specialization, because if we look at what we have in Pulse, we have all the information. And that looks a lot like the first limitation we solved. And it looks a lot like it, and we actually do some specialization here. So the question is, why do we need specialization? Well, only apply specialized is called, so we'll look at it. And in apply specialized specifications, we'll see that it says that it needs specialization. It says so, it's only calling block 7, so we look at it, and block 7's specifications also say that that function needs specialization. And here we can see why, because captured is an unknown block call. It is an unknown block call because, as we said, since the beginning of the presentation, captured variables behave the same as parameters. So they come from the outside. Block 7 needs to be told what is captured. We need to enforce that property, so we need to specialize block 7. In order to specialize block 7, apply specialized needs to know about captured, so it needs to have it in its specialization information, and it needs to know also the context of captured to be able to pass it down to block 7 and specialize block 7. The context of captured is known by the caller of apply specialized because it is a captured variable of apply specialized. So we get back to it, captured block. Captured block has all the information about all the blocks involved. So surely it can pass down the context of captured. But note that we only have one pair of brackets here. We only have one pair of brackets because all the specialization we saw happening in Pulse is actually happening at the same time. We do the specialization of blocks and arguments, blocks stored in objects given as arguments, and blocks in the captured variables at the same time. And even more so, by fixing this case, we'll also have the blocks in objects, in captured variables, and so on. Everything will work together. So there's only one pair of brackets. The only thing we had to decide is the order in which we have to give the captured variables, and they are simply given in the same order as the blocks. And we assume that captured variables come before arguments. So here, the first block we'll see is actually the field captured by value 0 of capturing, which is captured. So the captured variables of captured are the first one. The next block is capturing in the argument. So the captured variables of capturing are the following one. The caller respects the convention and the callee as well. So PTR comes first, then captured. And now that we have all the information about captured in apply specialized, we can specialize the call to block 7. And this can be specialized in the pre-analysis specialization. So we have the phases 1, 2, 3 happening here, exploiting the phase 0 as well. We have the new block 7 specialized created, and these blocks 7 specialized will replace the call to captured by a call to the block 6. And there we have it. We have completely specialized our case, our limitation. And because it is completely specialized now, exploiting all the information we have about the blocks, we have the right specifications for it. We now see that PTR points to 42 in the post condition and must be valid in the precondition. All right, so we've solved the limitations we've seen. Now time to conclude. With all the specialization, the one in the pre-analysis and the one doing pulses analysis, we now have 4.38 times the number of non-block calls we had without any specialization, and only 1.17 times the number of unknown block calls. Remember that the number of unknown block calls cannot be decreased because we are not deleting anything, but it only slightly increased, even less than using the syntactical specialization, like the delta is smaller here. So we actually increased the number of non-block calls 4 times faster than the number of unknown block calls compared to without specialization. And the result is that now we have 37.2% of the block calls that are known during pulses analysis on our millions of code. On a wider view on infer, well, this is specific to pulse, what we just saw to solve the limitations. So the solving is specific to pulse, but any analyzer that has the ability to work with closures could actually do it. All they would have to do is replace the phases 1, 2, and 3 of the pre-analysis specialization and do them during the analysis. And then everything will plug back into the pre-analysis specialization thanks to in-phase working. Measuring the impact on bugs found, we see that on a large Objective-C code base, 1.22% of the bugs found directly involve values created by specialized functions. Assuming they are not false positives, that means that at least 1.22% of the bugs are now fixed false negatives. I say at least because some values created or manipulated by specialized functions might be indirectly involved in a bug found if, for example, they decided on which path we're taking, which branch we are analyzing. And again, the specialization we do in Pulse is kind of cost-free. The impact on performance is negligible, whether it is from the technique itself, creating the callee and doing all the manipulations, or the overall analysis with the extra functions to analyze. I would like to thank Sunkun, Dolma, Daiva, and Jules for helping me with this work, as well as the rest of the info team, and thank you for listening.
Thanks very much, Quentin. I guess we can switch to questions. I can see one posted already. Akos, do you want to come and let me just vacate.
Can you hear me now? Corentin, can you hear me now?
I'm back.
To me, it seems like Corentin is muted.
Can you hear me? Hello? Can anyone hear me? Okay, thanks.
No. That's weird.
Is it working now?
For some reason, I still can't hear. I'm back.
Yeah. Do you hear me?
Nah, still can't hear.
Come on. I'll try to answer.
Yeah.
Is it better now?
So I'll read the Akash's question. The ratio of known to known to total blocks is around 37%. What are the rest? What's the reason for not knowing them?
Good question. Well, certainly there might be some functions that are simply not called in the call base. So we don't specialize them because we don't see any call, so we don't see any block given to them. And for the rest of the reasons, I'm not sure about them, so I won't say anything.
Okay, I had another question. So you mentioned that the performance cost was negligible on the. I am guessing that you mean that on the code bases that you run this analysis, the cost was negligible. The differential, the cost differential was negligible, I guess. Do you have any idea of how? I mean, that's surprising to me because it sounds like a recursive inlining to some degree, right? Guided but recursive, right? So I can imagine situations where this can explode, right, very easily. So I was wondering, what do you have any data or observations about how deep a chain of specializations could get? For
I
example,
don't have specific data to give, but at some point I measured how important, how prevalent are specialized functions in the code base, and they are not that much. That's all I can say, I think. I don't think I can dive into the details of the numbers have.
okay, thanks. Any other questions? Okay, thank you again. And going to be starting in 8 minutes. Next talk. Thank you.
Thank you.
Yeah, I think I would say let's wait just in case there are people who, are timed on the program. Sure.
Can you see my screen now?
Yes, you can see.
Cool.
Okay, I guess we can get ready bit by bit. So this is the second talk of this session and the last one. And this is a talk by Akos Haidu. I'm sorry if I mispronounce your name. And it's on a scalable and extensible static analysis for Erlang using Infer or Inferl. I'm not sure entirely about the pronunciation of that either.
Yes.
Okay, the floor is yours.
Thank you. Can you hear me and see my screen well?
Yes.
Okay, great. So thanks for the intro. And yes, indeed, in this talk, I'm going to talk about Infer, which provides scalable and extensible static analysis for Erlang. And obviously, it is based on Infer. And this is a joint work done with a bunch of other people from WhatsApp. So as I assume that most of you are familiar with WhatsApp. It's a messaging platform used by more than 2 billion people every day around the world, sending hundreds of billions of messages daily. And WhatsApp has three core values. It's simple, so that anyone can use it. It's reliable, so that messages go through, and it's also end-to-end encrypted for security. And at Meta, in general, we have various analysis tools that help people or help developers write robust code that satisfies these properties. But in this talk, I will be focusing specifically on the server side of WhatsApp, which is written in the Erlang programming language. It consists of millions of lines of Erlang code. And we do apply some static analysis, such as linters, type checking, or the dialyzer tool, which is shipped by the Erlang distribution. So we apply these to WhatsApp server. However, we found that these tools were not enough to provide analysis for all the properties that we were interested in. So in this talk, I will present how we applied Infer for the static analysis of Erlang code, and in particular to the analysis of WhatsApp server. I will start with a few examples to show what our tool can do. Then I will present the challenges that are associated with analyzing Erlang code. And I will also dive a bit into the details of how we do the compilation and analysis. And finally, I will present some results on running the analysis on WhatsApp server. So let's start with a few examples. On the left, you can see an Erlang code, and Erlang is a functional language. You can see a typical implementation of a head function, which should take the head, so the first element of a list. And for an empty list, it simply returns empty. And for a non-empty list, it takes the head, puts it in a tuple with awk, and returns it. And this empty and awk that you see here are actually called atoms. They are a commonly used construct in Erlang, and well, you can basically think of them as named constants, like similar to enumeration items in Java. So this is how you would implement a typical head function. And then you can see some examples of calling this function. For example, good will obviously succeed because it will match awk and 1 against the head function being called on this list, where 1 is indeed the head. But for example, if you look at this bad function, it will crash because it is expecting empty to be returned, which is obviously not the case for a non-empty list. Also, bad2 will again crash because even though it is expecting a tuple, which is correct, but the value 3 will not match what is being returned, which is 1, since 1 is the first element of the list. And since Erlang is a dynamically typed language, nothing prevents us from calling head with something that is not a list, for example, with the number 1, 2, 3. But again, this will obviously crash. And we can run infer with this command. Basically, pulse. The pulse option enables to use the pulse analysis, which has already been discussed in some of the previous talks, but I will also talk in more detail about this. And then after the dashes, you can see ERLC, which is the standard compilation command for Erlang files. And if you run this command, you can see infer's output, and you don't have to go into the details. The main point is that the three issues are caught. Basically, bad and bad2 result in a non-matching right-hand side, and very bad, where we call it the function with an integer, results in a no-matching function close. And these are some of the typical standard errors that you see in Erlang. And along these issues that I just presented, there are some more standard issues that we can detect. There are a bunch of examples here. You don't have to look at the details. The main point is that we can catch issues related to data types, such as accessing non-existing keys in a map, or treating something as if it was a different data type, and also related to all sorts of possible non-exhaustive pattern matches in different constructs, such as function closes, case closes, and so on. And we refer to all these issues together as reliability issues because these are the ones that would result in a crash runtime. And besides these reliability properties, what is probably even more interesting is that we also support custom user-specified properties. And for this, we use Infer's tuple analyzer. I will also get into the details of this a bit later, but basically tuple allows us to specify temporal properties using automata. As an example, let's say that we want to check whether or if ever it is possible to write to a file that has already been closed. And first, we have to formalize this property for tuple as an automata. You can see the automata here. It has 3 states. In start, we can loop, which actually means that this is a non-deterministic automata, in order to be able to track multiple files at the same time. Then in line 3, from start to closed, we go there if we call file close, and in the variable f, we remember the argument that we passed. And then we go to the close state. And finally, in the close state, if we see a call to the write function with the same file passed in as argument that we remembered, then we go to this special error state. And you can also see that functions in Erlang are identified by module : function name / the arity of the function. And then let's assume that we have some example code with 2 main functions, good and bad, both of them which in the end call or write to the file. But in the beginning, good calls nop, which doesn't do anything, and bad calls op, which actually closes the file. And you can also see from this example that we actually support interprocedural analysis for these user-defined properties. And similarly to the previous example, you can run tuple with a simple command. You specify that we want to run a tuple. We specify the property, and then we have the standard Erlang compilation command as from before. And you can also see that we will get the tuple error reported for the bad function, which is correct. As another example, consider that we want to do taint analysis. We want to know whether the value returned by a source function ever ends up as the argument of a sink function. We can specify this with a similar automata to the write after close. So from start, we loop. And then from start, we go to tracking if we call the source function. And in the dirty variable, we remember the return value. And then from the tracking, we go to the error if we see this argument appearing in a sink function. And you can see that we also support regular expressions. Basically, any function from any module with the name source and sink will match. But there is one limitation to this, though, is that we only match the exact same value, so we cannot really track transformations that is happening during chains of function calls. If we would like to do so, then we can also then we have to add all the transformation functions that we have. This is where regular expressions can help a lot. And right now we also have to add some other functions, starting with this underscore Erlang make. These are basically internal functions corresponding to data structures. So for example, when we construct a tuple or a list, we have these make tuple and make cons functions internally, but this is something that in the future we would like to hide from the developers. So let me now briefly mention some of the challenges that we are facing when trying to analyze Erlang code. But first, let's talk a little bit about the context. So Infer already supports a few languages like Java, C++, Objective-C, or also Ada and C#, as we see in this workshop, but they are mostly imperative or object-oriented as opposed to Erlang. And there are also a few built-in analyzers in Infer. In this talk or in this work, we are using Pulse and tuple. And finally, it is important to note that infer does a compositional bottom-up interprocedural analysis, which means that we analyze functions independently to compute summaries. And if some function calls another function, then we use the summary computed for that function. So in this context, the first challenge is that Erlang is functional. We have recursion, closures, and higher order stuff all around the place. And Erlang also supports captured variables. And since in Erlang there is no explicit variable declaration, we need to do scope analysis to determine if some variable is local or it is captured. And also, as discussed in detail in the previous talk, higher order functions are challenging in a compositional setting because if we analyze them in isolation, we don't know which functions they are actually calling. So if you look at this example, in lines 1 and 2, we have the standard map function, which takes some function f and recursively applies it to each element in the list. And if we analyze this map function in isolation, we don't know what f potentially can do, right? Then also below you have the main function where we actually call map, and we pass in a lambda which takes y as an argument, but it also captures x. And here we would need to figure out that x is actually not a local variable, but it is captured from the outside. Now, one challenge which is very specific to Erlang is the so-called let it crash philosophy, which means that basically in Erlang, it is quite hard to distinguish between errors that are deliberately thrown and runtime exceptions that should never happen. So for example, you can see this head function here, which will obviously crash for an empty list because it only has one clause corresponding to the non-empty list. But it will crash for the empty list, and it is not really obvious whether it is intentional or the developer just forgot to handle this case. And this is even amplified by the fact that we have supervisors in Erlang that can supervise processes and restart them if needed. So basically, they provide an extra layer of fault tolerance. And again, just by looking statically at the code, it is not clear whether something will be handled by a supervisor or not. Then I already mentioned that Erlang has dynamic typing, and that dynamic types are actually used quite pervasively in the language as opposed to most of the other languages in Infer. And as you will see later, we actually run into some limitations that we had to fix. And this is also connected to the let it crash philosophy, because pattern matching will be rarely complete. So for example, here you have a function which calculates the length of a list, but it is not exhaustive for other types other than lists. And again, it is not obvious whether it is intentional that this function crashes if we call it with a number or anything other than a list. Concurrency. Erlang was designed with concurrency in mind. It has built-in primitives for sending and receiving messages. In the example, you can see the receive expression, and the exclamation mark is the send expression. These are built-in and quite frequently used. And also, Erlang has high-level abstractions for concurrency, such as generic servers, event handlers, and state machines. And finally, we have scalability, which is a usual challenge in any program analysis. But I think it's worth pointing out here because WhatsApp server is huge. We have millions of lines of Erlang code, and we want to provide early signals to developers. And in general, Infer's compositional approach is quite scalable, and the under approximations that it does. But for example, for certain data structures, like lists in this example, we might need some Erlang-specific approximations as well, besides the general stuff that is already there in Infer. So let's now dive into the details of the compilation and the analysis. And as you will see, some of the challenges have already been addressed, but many of them are still ongoing work where we only have some plans. So you can see the architecture of Infer. there are two main phases. In the capture phase, the different front ends compile source code into Infer's intermediate language CIL, which is based on control flow graphs, CFGs. And then in the analysis phase, we can run different checkers to report the issues. And obviously, to support Erlang, we added an Erlang front end, and it relies on ERLC or rebar to compile Erlang code into so-called beam files. These are the binaries for Erlang. And if we provide a special flag, these beam files will contain the ASTs, the abstract syntax trees for the Erlang code. And then our front end can parse these ASTs. We do some basic validation. We do the scope analysis, as I mentioned, for determining captured and local variables. And then we do the actual compilation from AST to CIL's representation. And on the analysis side, we also had to add some custom models to PALS, like Erlang's data structures or some of the library functions. And as you will see, this is also extensible by user-defined models. And for the custom properties, we used and improved the tuple analyzer, which also takes the user-defined property, the automata that you've seen in the examples, as an input. And we can also extract specifications, type specifications from the standard library, which is called the OTP, to make the analysis more precise. I will get back to this a little bit later. And finally, when we have the issues, there is a reporting phase in Meta's CI pipeline, where we do signal boosting, we match against production data, and we determine ownership to ultimately raise signals to developers. So let's look at the compilation a little bit. We have this head function from before. Let's see how we would translate this into Infer's representation. So each function will get its own CFG with the appropriate number of arguments. Here for the head function, we will only have one. And then we will process each clause, clause after clause. First, we have to check whether the argument is an instance of nil, which is the empty list type in Erlang. If yes, we create the empty atom and we simply return it, ending the function. However, if it doesn't match, the argument is not a nil, then we have to check whether the argument is a cons, which corresponds to the non-empty list type in Erlang. If yes, we read the head field, we put it in the variable h, and we put it together with the awk atom in a tuple, and we return this tuple. Otherwise, if the argument is not a cons, then we don't have any more clauses, which means that none of the clauses will match, in which case we report the no matching function clause error. So this is how the translation works in a nutshell. Now, I've mentioned the challenges of dynamic typing and the let it crash philosophy. And what immediately struck us is that there are many false positives, or there were many false positives coming from non-exhaustive pattern matching. Like if you remember this length function from before, this only works for lists, and it is not clear whether this was the intention or not. In order to avoid reporting false positives for such cases, we rely on type specs. For example, this spec says that length is a function which takes an integer, takes a list and returns an integer. And WhatsApp server and also the standard library for Erlang is quite well annotated, so we can avoid these false alarms. But it is important to note that we don't actually do the type checking. For that, we rely on type checking tools. We just assume them to be true. And similarly, there are many standard library functions for which we don't have models yet. For example, lists sort. This would be by default a non-exhaustive pattern matching, because we are just prepared for empty or non-empty lists. But actually, if we parse the specs from OTP, the standard library, we can figure out that list sort is actually a function that returns a list. So this pattern matching is indeed exhaustive, and we can avoid this false positive. As I mentioned, Erlang also has various data structures. And for the bounded ones, like tuples or records, we have full support. For lists, we do approximation. In certain operations and library functions, we only process them until the loop unrolling bound, which is configurable in Infer. And for maps, we use a recency abstraction, somewhat similar to what is being done in Java. We only store the most recent key and value, which will basically allow us to say that a function is fine when it checks first the existence of a key before actually trying to access it. But if we forget this check and just try to read the value at the particular key, then we can report the error. As for the functional aspects of Erlang, currently we support closures in a limited way in a local context. And as I already mentioned earlier, since Erlang doesn't have a notion of variable declarations, this requires a scope analysis to determine which variable is captured and which is local. And by implementing this, we actually found an inconsistency. If you look at this example here, it's a binary operation, something plus something else. On the left-hand side, you can see x equals 1, which will assign x to be 1. And on the right-hand side, you see that there is a lambda defined, which will assign 2 to x and then call the lambda. And if we put this in the interpreter, it processes the two sides of the plus operation as independent. So the whole expression just simply returned 3. But if we would compile this code and try to run it, the compiler processed it from left to right. So it made the x inside the lambda captured variable, which already existed from the outside. And since 1 is not equal to 2, it would result in a crash. So we actually submitted an issue to GitHub, and since then it was actually fixed, and it was basically the interpreter which was right. Now for higher order functions and recursion, we don't have support yet, but we do have plans. And while it was discussed in quite a lot of detail in the previous talk that the challenge with higher order functions is compositional reasoning. When we analyze a function, we don't know about the potential closures it can receive as an argument. And one way to solve this is specialization, which was pretty much detailed in the previous talk, but just to recap, basically if we have a function g that calls some function f that we don't know about, but then in some main function we see that g is called with some concrete f, then we can create a specialized version of the main function and for G. And since this is already existing for Objective-C in Infer, we have some plans to use this. But another approach could also be defunctionalization, which is basically a whole program transformation that removes higher order functions while keeping the semantics of the program. I'm not going to go into the details of this, but there's an article if someone is interested. And as for recursion, we could either do a fixed point computation, which was actually there in Infer previously, but it was removed because usually developers were happy by the issues reported only computing one iteration for other languages. But we might have to bring this back for Erlang. And alternatively, for certain cases like standard library functions, like, for example, mapping over a list, we can actually provide some custom models that would basically avoid recursion at the very first place. And as I mentioned, Erlang has built-in primitives for concurrency. For example, in this function f, you can see an example for a receive expression. We can receive tuples of a sender and something. And if this something is an integer, we add 1 to it, and then we send it back to the sender by using the exclamation mark symbol, and otherwise we just send back the oops atom. And here's an example using the shell. We can compile and spawn this process, and then we can send a message with our own process ID and 1, and then in return we will get back 2. Now, right now, send is modeled as a no operation, and receive is modeled as a non-deterministic choice, but we have some plans to support this as a generalization of function calls. Basically, we have to connect which send can correspond to which receive. This can either be done by some pre-analysis or even under-approximated by a dynamic analysis. And then we can create summaries for receives that we can use whenever we see a send. And also, similarly to mutually recursive functions, if there are two processes sending messages back and forth, we might need to do some fixed point computation. And the standard library, OTP, also supports various higher level abstractions that we don't support yet, but again, for this we have some plans. For example, there is a Gen server, which is used commonly to implement distributed objects and actors. Basically, you can see the typical flowchart in the slides. You can spawn and initialize a server, and then it runs around in a loop, receiving calls until we kill them when it is exiting. And this is very similar to objects, basically creating an object, calling methods, and destroying objects. And for objects, Infer already has support in other languages, so we could try to reuse that. Now, Erlang also has a very extensive standard library with lots of utility functions. And for some of them, we already provide models, but for most of them, we just use the type specs, as I mentioned earlier, for lists sort, so that at least we know what is the type of the thing that they return to avoid false positives in pattern matching. But we also give the possibility to define custom models, not just for library functions. For example, in the infer.config file, we could say that this given function in this given module with this given arity should have the following behavior. It should return a tuple with the atom true and null, which means something non-deterministic. So basically, this is equivalent to if the function had this code. So this complicated function returns a tuple of true and something non-deterministic. And in the future, though, we plan to have more behaviors apart from this simple it returns something, and we plan to make it. We plan developers to be able to define this in a more user-friendly way, so not this JSON syntax. And I've also mentioned that for the user-defined properties, the automatas, we used and extended tuple. So tuple already existed in Infer, but so far it hasn't yet been deployed at such a scale when we used it for WhatsApp server. And when we were running it on WhatsApp server, we actually had some scalability issues. Basically, we hit some internal limits during exploration of abstract state, which means that some valid states were discarded. And in order to mitigate this, we implemented a bunch of things, some more expensive normalization procedures, which are triggered selectively when this limit is about to hit. We added support for dynamic types in tuple solver because, as I mentioned earlier, dynamic types are quite pervasively used in Erlang as opposed to most of the other languages. And we also provided a garbage collector to discard those states that refer to variables which are not in scope anymore. And these all helped to discard infeasible states, allowing us to hit the limit later and to be able to explore more valid states. And finally, let me talk a little bit about the results that we got so far. First of all, we developed an extensive set of small test functions, each of which exercise a specific feature and then either terminate successfully or deliberately crash. For example, here in test add awk, we add 2 plus 3, and if it's 5, then it's fine. Otherwise we crash. And in test add bad, we again add 2 plus 3, and if it's 5, then we deliberately crash. Otherwise we don't do anything. And we compile and run these snippets, and then we also analyze them with infer, and we cross-check whether the results match. And obviously, if the results do not match, then we either have false positives or false negatives, assuming, of course, that the compiler is correct, which is not always the case, as seen by this issue that we submitted. And more interestingly, we have also deployed infer to Meta's CI to continuously run on WhatsApp server's code base. And initially, we found many false positives with the reliability properties. This is something on which we are currently continuously working. But with some custom paint properties, we actually achieved quite promising results. We found 200 issues, and we matched them against production logs to filter out false positives, which resulted in 21 issues being surfaced to developers recently. And 3 of them have actually been already fixed, including one which had a very high priority among developers. And we also already deployed signal boosting. There is also a dynamic analysis based on FOSTA running on WhatsApp server. If you're interested, you can check out the paper. It was recently presented at ICST. And the thing with signal boosting is that if one tool already found an issue, then the other tool will boost this signal and add any extra information that the other tool doesn't have. And here, obviously, the main challenge was to actually match the issues found by the 2 tools. So let me wrap up. I presented infer, which provides scalable and extensible static analysis for Erlang. We support many of the standard reliability issues, but we also allow user-defined custom properties. And I've mentioned some of the challenges associated with analyzing Erlang code, Erlang being functional, the let it crash philosophy, the usage of dynamic types, concurrency, and obviously scalability. I talked a little bit about the front end, how we do the compilation, and I also talked about our extensions to the pulse and the tuple analyzers. And our initial deployment shows very promising results on WhatsApp server with some detected issues that were already fixed by developers. And the parts within infer are available open source. So yeah, thank you for your attention, and I'm open to any questions.
Thank you very much for the talk, Akos. Can you hear me?
Yeah, I can.
Okay. So, are there any questions for Akos? Well, while we wait for people to queue up at the chair spot or Slack, I have a question. You mentioned type specs and how you use them to as assumptions regarding the types or shapes of your values. Do you propagate out things that you learn from, or rather, type specs of collies in case you don't have type specs for the caller? If that makes sense.
Yeah, that does make sense. So if there is a function that doesn't have any type spec, so it doesn't mention what it returns, but we know its body, then we analyze that function, and we will in the summary will include the potential types that it can return. So in this sense, we do propagate this information, but it is, I would say, it's not directly related to type specs.
Okay, well, I mean, is it do you propagate that back to your preconditions? Is that a form of abduction? In other words.
Oh, for the preconditions, yes, but we so what we do with these type specs is we assume them. So if the function is called with some types other than what it should be received, then currently we do not explore those parts of the program. For that, we trust that the type checker would catch these kind of issues. So we don't want to compete with the type checker yet. We are just assuming that information. But for example, if you have if you pass some value to a function which has the type spec which says that it receives an integer, then later in the callee, you would know this information that, okay, since I passed this value to that function, it has to be an integer. So this is propagated again.
I see. We thank you for the answer. There's a question by Matthew Jin as well. He says, you mentioned that you translate from the AST. Do you find that the Erlang frontend has to deal with additional complexity resulting from representing the syntactic sugar?
Oh yeah, that's an excellent question, and yes, by working on the Erlang AST directly, the translation or the compilation that we have to do is obviously more complex because we have to deal with all the syntactic sugar like list comprehensions or records and this kind of stuff. As opposed to, like, alternatively, we could also use, for example, core Erlang, or maybe just the binary format in the Beam file, which is a lower level. So we would have to deal with less kinds of constructs and syntactic sugar. But we had various reasons why we discarded these approaches. And one of the main reasons was that it is a little bit further away from developers as well. So for one, if we want to report issues, then we would need to come back. So we would have to back propagate the issues to the original level of Erlang code. And I think what is even more important is if we want to provide custom models or custom abstractions, then it is easier or better to do on the level of the Erlang AST. But this was obviously a choice that we had to make, and there were both advantages and disadvantages, but ultimately we decided to go for the Erlang AST, and I feel like so far it's working out quite well, and I think it was a good choice. Obviously, there's some syntactic sugar that we do need to handle, but I would say that Erlang is still a pretty small language in this sense that it's manageable.
Thanks. There's another question. I'm afraid I might mispronounce this name as well, by Bikian Cheng. I have questions regarding the custom models for standard libraries. There are some standard libraries containing implementation of system calls. For example, UClibc contains send to and socket, etc. their implementation are written in assembly code, which causes some issues to other tools because they cannot be recognized by the tools. I'm curious if Inferl is able to handle this assembly code implementation as well.
Right now, no. I mean, we have custom models for a few library functions like list append or map get and things like that. But I think those are probably not written in assembly. I would say that even if we would be able to handle assembly code, maybe that would not be the best choice, because I would say at this level we do not want to deal with like system resources. Like, for example, as I mentioned, like Erlang has built-in support for send and receive, but most probably we would like to abstract out this detail of like sockets and network communication. So I would say that the purpose of providing custom models would not just be the fact that we might not support assembly code, but also to provide meaningful abstractions. Hope that answers the question. Also, let me add that I think many of or some of Erlang's library functions are written in C, and in theory, since Infer also supports C code, we might be able to analyze those. But again, I'm not sure if analyzing those functions would help. Maybe providing some custom models would provide a better approximation.
I see. Thanks. Are there any other questions? I can't see anyone typing or approaching the session chair podium. So thanks very much again for that lovely talk. And I'm guessing this is when people break for lunch.
Yeah,
so
perhaps it's dinner.
Or go to bed, yeah, exactly, depending on the time. So
yeah, thanks for the opportunity. Also, thanks for the questions, and I will try to hang around Slack or Gather. So if anyone has more questions, then feel free to reach out to me offline.
Cool. Thanks very much.
Bye.
Can you share your screen?
Yes, please.
All right. So, shall we start?
Yes, please.
Great. All right. Next speaker is Locke, who's going to talk about incorrectness logic in Infer. Go ahead, Locke.
Yes, thank you very much for your introduction.
No, wait, we can't hear you. Can we? No.
Do you hear me?
It's very quiet.
Hello? Hello? Sorry, please confirm. Do you hear me clearly?
Oh, yeah, we can hear you. It's very quiet.
Yes. Hello, everyone. I'm Quang Lộc Lê.
Anyway, you can put your mic louder.
Yes, I did. Do you hear me?
It's very quiet.
Do you hear me, Zeus? Okay. So, hello everyone. I'm Quang Lok Le from UCL. So today I'm present who's as a checker in developing Infer Facebook. So this is a joint work of with Angela, Zeus, Josh, Derek, and Peter. So I'm starting my talk with the first axiom of a bucket chain tool at scale by Peter Ohans, the founder of Inverse tool. So Peter say the axiom say that don't spam the developers with phone positive. So my experience with OpenSL developers so that developers are very sensitive with the phone positive. So our tool put as found 41 bugs and 15 of them was unknown previously. So we commit the fix and all the bugs we found to the OpenSL developers. And one of the bugs and the fix we present here. So this bugs in the function prepend. In function prepend, first in the line 956 here, it's called the malloc malloc. That is the malloc wrapper to allocate a memory and assign the pointer to the pointer x. And after that, it will reset initialize all the content of the allocated memory with 0. Our tool finds that if the fmalloc return null, so the memset will return the null pointer errors. So we report the bug to the OpenSL, and one senior developer at OpenSL say that, okay, that's in phone positive. And we also say that if we want to fix the bugs, so we need to check whether the pointer x equal to null, we just return. But the developer say that the malloc wrapper never return the fail. So that means this is phone positive. So this one is not the only one we see. More than 60% of what the bugs we report, developers say that that's phone positive. And I'm quite nervous. I'm rerun the tool and check the error trace. What happened there? And in the error trace of the infer tool, our tool, PoolAsh, it say that actually when we call in the prepend, first we call the fmalloc, and the fmalloc will call the OpenSL malloc. That is the main malloc. It's very similar to the malloc in the standard library of C. And OpenSL malloc may return a null pointer. So everything we report is correct. But why the developer they say that our report is phone positive? And we don't want to watch the developer instance. So I do a graph search, and I find that actually in OpenSL there are two fmalloc. So under the fmalloc in the folder apps lib apps.c, and inside this one, every time the OpenSL malloc return null, it will abort. So it's not return null. So he is right. There are another function, and we think that he confused between the two fmalloc. And I showed the log and everything to the developer, and he agreed that that's a bug, but he not accept our fix, and he creates another pull request to change the fmalloc to make the two fmalloc consistent. So you can see that if you just report the phone positive, they very instance. So our tool, we develop a tool called PoolAsh, a bug catching tool, and we prove the presence of the bugs. And our tool is precise. We don't spam the developers too much. And it's also scalability. So it's based on production, and it can support the bugs review, code reviews, continuous integration CI system. And our tool scale at 3-dimensional scale. So it can support very large code space in a big team without thousands of developers and very high velocity. That means every day, every week, the team can commit around 10K of diffs. So our tool is based on infer. So what is infer? Infer is a tool based on the paper in Popo 2009. That's a compositional shapes analysis by means of bioabduction. So infer can analyze the whole linear kernel less than 30 minutes, and also less to infer also acquired by Facebook in 2013 and very successful in both academics and industry. But we find that infer has two main problems. The first about the foundation, and the second about they don't have any box reporting mechanism. So we will discuss it further and how our system fits the two disadvantages. The first one, clash with foundations. So we talk about through the presence of the box. So we talk about under approximation and over approximation. So when we say that we want to find a box, we talk about under approximation tool like symbol execution in CLI or symbolic model checking in CBMC. So those tools, they analyze the whole programs starting from the main function and try to describe an approximation with each subset of actual programs behavior. So as such, when it's report a box, that box is a true box because the approximation also always inside the two programs. But the disadvantage is very long-standing problem with explosions. And second, they don't have any clear memory model to support the symbolic heaps. In another words, another test is over approximation reasoning. That's in the infer, that's the proposed by abduction. And by abduction, that means they can begin anywhere based on the summary of function, pre-condition, and post-condition. They can begin anywhere. And because they can begin anywhere and it's linear in the number of functions in programs, it's very scale and it has a memory model based on separance logic. But because in first, they describe the approximation is over approximation of actual programs. So when it's fire box, this box may be inside the actual program or may be outside the actual program behaviors. So that means it may report false positives. So we put two kind of techniques together, and you can see that under approximation, it can report two box but not very scale. But over approximation in infer is very scale, but maybe false positive. So how we can achieve both scalability and also precision? So we may think about under approximation analogy of infer or compositional by abduction of CLI and CBMC. And for the memory models, we can say that we have under approximate analogy of separance logic. Actually, this one, there are some words already, that's the incorrectness separance logic. So our solution in this course is the first one. That's the under approximation analogy of infer. And we use incorrectness logic, separation logic to model the memory in the heap. So what is the compositional reasoning? So that's the analysis result of a composite programs is defined in terms of the analysis result of its parts and a means of combining them. So what's the analysis result? What's the parts and what's the mean? So a part here is a function or procedure in program. So it means given programs, we will develop dependencies called graphs of a function. For example, in this programs, we have two components of a code graph. In the first one, we have f1, a function f1, called function f2, f2 called f3, and f4, and f3 is self-recursion function. And what is the analysis result? The analysis result is the under-approximate summary specifications, that's the incorrectness triples. And a means here is under approximation by abduction. So we will go through all the item here one by one. So what's the under approximate triple? That's it. And we have a triple P, C, and Q. P is precondition, C are programs, and Q is postcondition. So the meaning of the triple is that for any state S in the postcondition, S can be reachable by running the programs on some states in precondition. And in correctness triple, we add the status here, the epsilon here, to annotate where the program is okay, that means it's executed normally, or there are some error that abnormal execution. We give two examples in the triple, incorrect triple. The first one, that's the okay triple. So we call the free, that's the specification of the free wise. So if in the free condition, wise has been allocated. So if we execute the programs, so in the post condition, wise will point to invalidated heap. But in the second example, in the free condition, if y point to invalidated heap location, so we will come with the post condition with an error. That's a double free error. So that's a two kind of okay and error triple. And what is the analysis problem? The analysis problem is when the input of programs or control flow graphs, and on the specification of the atomic procedure or command in the program and libraries. And the analysis will answer the question, find all the specification of the programs and function in the programs in the bottom-up manner, in the bottom to the left to the root of the dependency control flow graphs. And it's do it by abduction, under approximation by abduction. So it's based in the infer, the original infer, the over approximate by abduction, given a presumption A and the conclusion G. It will infer the missing information in the free condition and the frame in the post condition, so that A star M, star here is the separating conjunction. A star M imply J star F. But under approximation is imply A will star F. That's the frame here will go to the free condition, and the missing information will go to the post condition. So it reverses with the over approximation. And if we can say that we infer on the specification with error and okay, how we can come up with the mechanism to say that which the error space is the toolbox. So for example, in this example, we have a function f with the parameter x, and we say that we want to assign the content of s equal to 42. So do you report a null pointer difference here? So without considering the entire programs, how do we know about E2? So in infer, it use some heuristics. So when it cannot give safe proofs, and it's based on the pattern of the code around it will decide where does the bugs happen or not. And also in UC glitch, also use some kind of heuristics. UC glitch is the state of the art of the simulated execution. So first of all, it's use some heuristics and also not very successful because it can report around 11 real bugs and a loss of false positive, and the fix rate less than 3%. And in our system, we will infer the specification of function, and we define some definition to say that whether the error space is the toolbox or not toolbox. So I will give you some intuition based on what we are finding. The first one in the first example here, that we come back to the example we report to OpenSSL. So we say that in this function, it's called a malloc, and the malloc may return null, and the mem set may cause a null pointer error. So the null pointer error is only in the prepend this function. So it don't have any condition, so it can happen without any context. So any function call the box will happen. So we call that's a manifest error, and we will report this kind of box. In the second example here, you can also say that we have open SL malloc here. It's assign the pointer to the data, but under condition the count equal to 0. And on here, it will assign the content. It will reference the data here. So this null pointer error here only happened when the count equal to 0. So we call that the latent error. So the error only happens under some condition. And for example, if we have another function, the main function, so we have a count equal to 0, and it's called this function, the chop up arguments function. Now the condition match, and it becomes a manifest error. So we will report the box in the main function. Okay, so actually we formalize what we find in here. So we say that an error triple P, C, and Q here manifest and will report to the developer if the precondition, we don't have any condition, and the post condition should be satisfied. That means we don't want to report that code. And other condition also say that the two last condition to make sure that we have a consistent post condition. So you don't need to understand that, but actually just intuition that the Q here should be satisfied with any the calling or context. And the last part of my talk about the implementation. So in the implementation, we say that we have some kind of mechanism, very strong mechanism to report, to classify whether the error spread is real box or not. But actually, that's it. In scientists, it's not much with the engineer. So like Tony said that scientists see perfection and idealist, but engineer is not the case. So we need to be realistic, as you have to compromise between conflicting interests. So in real life, in the real programs, we have lots of problems. We have to consider, we have to choose between the speed and precision. If we say that we have a SAS solver very strong, very complete solver, but actually in the real program, it's not complete. So we have to choose between speed, precision, dumb but fast, or smart but slow. And in the implementation, we choose the first one, dumb but fast. And we implement some solver, it's not complete solver, only for equality. And also in the so-called loss of pointer function and null function, that's our system not complete. So in real life, PoolS might produce false positives. So we do evaluation in the dataset of OpenSL and 8 open source C++ project developed and maintained by Facebook. And we classify the box found by our tool, and we compare with infer. We call the box is true box if the box has been fixed by the developer. Pending box, that means the fix had not accepted yet. And false positive, that means we could not find a fix. So the fix rate will be the number of true box of total issue found by the tool. And our experimental plan is run PoolS and infer on each project, collecting timings box found. Second, scalability, we compare the timing. And the last one, we compare the precision. We want to find which one has a better fit rate. And we try to answer 3 hypotheses. The first one, OpenSL compatible to on OpenSL, PoolS and infer is compatible. The second hypothesis, PUN-S can find some new bugs. And the last one, PUN-S is compatible with Infer due to the performance, in terms of performance. For the first one, we choose OpenSL 1.01 hash. We choose this one because the original Infer up to 2015, it can found or could found 15 bugs. And OpenSL has around more than 8,000 procedure and with around 400 K lines of code. And a result, PUN-S can find 26 issues. And 19 issues was the fix rate is 73%, and the fix rate of Infer is around 49%. And that means actually we say that our tool can find better fix rate than Infer. So we say that the hypothesis one can be confirmed. For the second one, we said we try to answer the question whether PUN-S can find the new bugs. So we run it in the OpenSL, the new version, the current version of OpenSL. This version has around 23,000 of procedure function, and PUN-S can find 30 issues, and only we report around 15 to bugs and 5 pending. Pending just means we report, but it haven't fixed. And the fix rate around 15%. And we report all the bugs we found, also the fix in 3 pull requests here. And when we say that we have a fix in every box, when after we apply the patch and we rerun the PUN-S and we check whether the bugs disappear or not. And on Infer, the current Infer, it can find 116 issues, and 7 of those overlap with us, and 40 is false positive, and the rest we haven't checked. And the fix rate of Infer may be around 1% to 65%. And in overall, you can see that the fix rate of PUN-S is around 61% and Infer around 23 to 59%. And for the last one, we compare the performance. So we compare in OpenSL 2 versions and 8 other C++ projects. And you can see the configuration of the project in here. We arrange in here you can see that line of code of some project may be small because we only count the code of the project and not count the library. But if we count the library, it may be very large here. And the last column that also include the library is used. And you can see that the performance in the column here, we list the number of minutes 2 tools spent on. And you can see that actually in the blue colors, we run our tool PUN-S with every function only include the maximum of 10 IL triple, increment triple. And in the gray color here, the column show the timing of the PUN-S in 100 IL triple. And the yellow ones is the timing of Infer. And you can see the timing of the PUN-S 100 can compatible with Infer, a bit smaller than Infer. Before I close, go to conclusion of the talk, I go to another story when we interact with OpenSL developers. So we report another box, the memory leak error in the function W body. That's the server, SL server, and we say that if the push here, line number 6 here fails, and IO, the first parameter here, equal to none, and the second parameter is not equal to none. The list happen, and we propose the fifth part is that we add one more line here, that the free for SSL bio. And when we report to the developer, and they said this isn't sufficient. The IO and bio chain include this one, so they will be double free. The correct fix is to set SSL bio to none. Here, he proposed the fix here. So, do you think that the developer proposed fix is a good one? So we apply his part and run our tool, the PLDI, and it say that actually if you push a none here, the list occur after this assignment. Okay, so if it's successful, so the list will happen here because we assign the none into here. Okay, so we report what we find to the developer, and he accepted our fix. So for conclusion, we talk about the PLDI, a scalable compositional box finding tool, and we use under approximate by abduction and a theorem about two positives to classify the error specification to whether it's true box or not. And we do some experimental to say that PLDI can find 41 bugs and 15 of them was the new bugs. And our fix rate might be 3x higher than infer, and it can as scalable as infer. So for future work, we are working on actually there's some direction we can working on a compositional simple execution or body model checking. That is the second option I discussed before. And the second one is the bug finding tool for concurrency programs. And the third one is how we infer the invariant of the loops so that now we can handle the loop properly. And the last one, how we can generate a test case to confirm the box in the case that there are some unknown function or function pointer our tool cannot classify that in a manifest error. So my talk end here. Thank you very much for your listening. Any question, please?
Hello.
Hello.
Yeah. Hey,
Yes.
Thanks, Locke, for the talk. This is Joe.
Yes.
I'm talking from the room now. So let's see if we have questions in Slack. Any questions in the room? Okay. Oh, yes. Can you state your name and your question?
Hi, I'm Simon, and the question is, you showed us the slide with the comparison to bi-abduction, where you showed how sort of the frame and the anti-frame basically switch sides on the entailment. Do you use the same procedure then to compute them, or sort of how do you get them, the frame and the anti-frame?
So your question is about the bi-abduction. Under approximate bi-abduction compared to the over approximate bi-abduction, right? Actually, we implement a new under approximation bi-abduction, and about the implementation. So we need to match the current context of the caller with the free condition of the function call, and we find the frame there. So the frame will be forward to the precondition of the function call, and after that we bind in with precondition will be forward to the post condition of the callee, and we use the information of the callee, the post condition of the callee, to combine with the current context to get the post stage, the post condition. I'm not sure that that's what we had done. for the under approximation biabduction. And actually, we implement a new one. We not reuse the one in infer.
Okay.
Yeah.
Thank you, Simon.
Yeah. Thank you very much for your question.
So I have a question. Can you clarify the relationship between pulse X and pulse? Because we've heard some talks about pulse this morning.
Actually, pulse S and pulse S. I'm not sure because pulse S Zeus developed it, and I'm not sure Zeus has any publication or any document. Or actually, Zeus has some document, but I'm not sure had any publication. But it's not the incorrect logic, and pulse S is pulse plus incorrect separation logic. So what we develop is on top of pulse.
Okay.
Yeah. Is it correct, Zeus? Is this fair for you?
Yeah. Just about the true positives theorem again. I'm really curious about the kinds of guarantees that pulse X provides versus biabduction, which, as you mentioned, is more heuristic based. I'm particularly interested in the theoretical guarantees.
I'm sorry, I don't hear the question clearly. It's very.
I'm particularly interested in the theoretical guarantees that pulse X gives. So could you summarize them again, as I didn't quite catch them the first time?
Yeah, the theory is here that you want to ask about the theory about the bug reporting, right?
About the true positives theorem.
Yeah, true positive theorem. So for the true positive theorem, we say that when the system is write an error specification, and under some condition, for the condition say that for the precondition of the error triple doesn't include any condition. Also, the post condition is satisfied. Satisfied, that means it's not the dead code. And also, some quantify if inside the post condition should be consistent. Also for satisfied. That means any function, any callless or context callless call this function is don't match the post condition unsatisfied. So that if such condition wouldn't here, that means the error specification will imply that the function contain a box. That's in my answers. Not sure that's clear enough for you.
Thanks. There's a question on Slack. Akash asks, is Pulse X implementation available?
Yes, I think it's online because it should be in infer repository. Yeah, you can find the source in the infer GitHub. Yeah.
There's some version of Pulse X in infer, but there's
some person. Yes, because now it's involved a lot.
Okay, thanks a lot, Locke. We have a few minutes of. One more question from Matthew. Jin.
Could you also talk about a bit more about the how the resource leak analysis specifically evolved in Pulse compared to how it compared to the original implementation with biabduction framework?
So in biabduction papers, they I think it's very clear that in the biabduction original paper, infer paper, you want to talk about the infer paper. Actually, the infer paper, they don't talk about any mechanism, any formalism to report a box. Because infer is supposed a tool to prove that the program is safe, not the theory. The theory is not in infer that couldn't tell anything about the bugs, right? And our work, I think the main contribution is about the true positive theorem. We can say that we define the error specification, error chipper, and we can say that when the error chipper is a bug or not a bug, a manifest error or not manifest error. I think that's the main difference between infer and punch ask.
Thanks. There's one last question, I think, from Esgi. Is Pulse X the same as Pulse ASL?
Yes, I think there are still some Pun S and Pun SL. Yes, I think the same version, but not all the code I committed to the Pun S because I think there are something very. I developed the system in last year, around last May, and when I finished the work, I commit almost everything there. But when I commit in around August or September, I commit the code in the GitHub, and there are the system, the infer framework, it changed a lot. So I had to change the system so that it can work in the new version of infer framework. But actually, the original code in the still in the artifact evaluation of the OPSLA paper. So, but I don't think the change is very much. Just around 90% of the push S is push ISL. 98%, I should say that. Is this clear? Yeah.
All right. Thanks a lot, Luck.
Yeah, thank you very much. Yeah.
And thanks for tuning in so late from London. So,
yeah, I'm sorry that for the problem of the connection or something. Yeah.
No worries. We still end up on time. So thanks. And now let's set up the next speaker.
13 sections. Okay. Yeah. Perfect. All right. 1, 2, 3. Hopefully, everyone can see and hear me in person and virtually.
All right, we're back. It is my pleasure to introduce our next speaker, Ilya Sergey, who's going to talk about hippodrome. So I assume something about horses.
Very well. All right. Thank you so much, Julian. Thanks for organizing this workshop. It's quite exciting to hear the talks here and be able to present our work. So, first of all, this is a work that has been quite long, actually not that long in the making, but almost 2 years in the publication process. So I very happily can announce that now it's coming out in the Transactional Software Engineering journal. So the main workload has been carried out by Andrea and Abhishek, who both are postdocs at the New York School of Computing, along with Sigmund and Kishore, who are undergrads, and my colleague Abik, Richard Kuri, and myself. All right, so let us talk about concurrent races and why they're bad. Well, okay, so races are in general very unpleasant phenomenon that can lead to badly predictable outcomes of concurrent programs and other nasty consequences such as memory corruptions and undefined behavior. So, one of the biggest discoveries of trying to do the race detection at scale is that many of them are actually not that very sophisticated in their manifestation. They're just something that programmers have missed or didn't think about. For example, they had a perfectly, so hopefully it's visible. So they had a perfectly nice class, Java class account with an integer field and the getter and setter to balance that. And that worked fine sequentially, but now they decided to use that concurrently in a program that does something like this. So, for example, it withdraws from an account, and for that it looks at the balance using the getter, then it subtracts, and then it uses the set. So now if we run this method withdraw concurrently in more than one thread, we get a data race. So specifically the two threads will interfere and the update in the balance might be inconsistent as in you can imagine some data might be lost. For example, the balance might not be updated to the total of the two withdrawals. So, so how do we capture the notions of data races more formally? There is a very rich body of research in concurrent data races, and many works, they look at the dynamic interpretation of this phenomenon, namely what happens regarding the reads and the writes into certain shared pieces of state, like this balance field of the account class we have here. Okay, so and here we have a number of read operations and write operations. So specifically, both threads that are executing withdraw, they perform reading to get the value of the balance, and then actually they perform reading again, and then they perform writing. So, and the data rates happen because some of these events, they happen to physically overlap in time. So, for example, the write, when the first thread sets the balance to the new value, might overlap with the read of the second one, and the two writes might overlap as well. And these are, like, there are multiple interpretations of what exactly is the atomicity of the read in the write, but unless balance, in case of Java, is marked as volatile, or we have some specific atomicity assumptions, we cannot even presume that reading and writing of the variable is atomic. So whenever we have a situation when they might overlap in a non-trivial way, that might be a race, and this is actually considered to be a race. All right, so the formal definition that you get from the books on the concurrency, such as the art of multiprocessor programming, is that data races are manifested is in the case when we have two unsynchronized concurrent accesses to the same memory location where at least one of them is a write. So the two reads are not considered to be erased, which we can witness in the real life. So many people can read from the same board. There is no conflict. But if the board's message is being modified at the same time, well, bad things might have happened. So, and there was actually quite a lot of work on the detection and repair of the data races. So on the detection side, specifically the Infer suite comes with a series of analyses under the name of RacerD. And those analyses are really good in detecting data races. But what is not present in this suite is the mechanism to turn errors into the fixes for concurrency. And that was kind of an idea that my colleagues and I decided to follow, which was very simple on the surface, but then obviously the devil was in the details. So, and it was not exactly very trivial to go from the static analysis that reports the races to an automated tool that fixes them. And this was our goal. So in this talk, I won't be focusing about on how exactly Infer detects the races. I will be focusing on how we turn the information derived by Infer into fixing those races, either automatically or with a human in the loop. So actually, that was one of the biggest discoveries of our work, that the tools that are concerned with data race repair, they are, folks, is it right there? Yeah, I'm sorry. Yeah, all right. We should do it? We should be good. Okay, wonderful. Yeah, let me know if there's something that needs to be adjusted. Okay, so one of the discoveries was that in the field of program repair, there is actually surprisingly little attention to what is happening in the field of static analysis. So when we started to survey the works that work on data races, we noticed that most of them, they actually rely on dynamic execution. So they take a test suite, they run concurrent programs on as many test suites as they can to try and to cover as many concurrent interleavings in this possible interaction graphs as possible, and then somehow extract the bugs from that and turn that into a bug fix. So on the other hand, well, there are static analyses that try to over-approximate all the behaviors, and those usually suffer from quite a precision loss. So what exactly the precision loss means for repair? Well, that means oftentimes you will be fixing non-bugs. And this is also something that is not very desirable. So you probably don't know these tools because they are like mostly prominent in the software and engineering community, and none of them has quite reached production. So the state of the art in program repair for concurrency is the tool pfix, which was published in 2018 at AZ. And that one uses static analysis and also with some combination of symbolic execution using Java Pathfinder. And the one which is based on the static representation and compiles programs, small concurrent programs into some version of Petrinets, and then uses that for bug detection and repair. That's the tool called Grail by Omer Tripp and others, published at FSC 8 years ago. So clearly there is quite a lot of gaps. So in terms of static detection, there was a lot of work on static analysis, and in terms of dynamic detection, well, so the reason for dynamic detection, so the reason why we are not very optimistic about dynamic detection, because first, many bugs are missed, and second, those methods are fairly expensive. So you cannot quite run the dynamically detection-backed program repair tool as a part of the continuous integration. So, okay. So in fact, this is the usual picture which appears in the talks about Infer and the analysis from Institute. So if we can focus on a particular class of bugs, such as true data races, so if we go with the dynamic analysis, we are going to miss loss of these data races, and also in terms of like when you come to concurrency, dynamic analysis, they're actually very, very expensive because we need to run test many times trying to cover most of the interlinks. All right. So if we do static analysis, then we ought to have many false positives. So a famous trade-off that is usually cited when we talk about the suites, the suite of Infer tools, is that they fall slightly kind of in this category. So they are neither sound as in the approximation nor complete as in under approximation, such as dynamic analysis, but they still manage to capture most of the bugs, and most of these bugs are true. All right, so, and they also come with added benefits of compositionality and scalability, and that's why you can run Infer as a part of your continuous integration. So RacerD, which was published at OOPS 19, and this is work by Sam Black, Cherny, Virgianis, Peter, and myself, actually fulfilled that promise, and it was very scalable, and it gave high signal, even though it didn't have formal soundness and completeness guarantees, we actually provided completeness guarantees in a POPL paper, which was following for a certain modified version of RaceRD. But RaceRD itself was quite successful, well, at least in Facebook, but hopefully even beyond that. So it almost didn't require any annotations. It was scalable and it was interprocedural. So obviously we tried to see if we can easily adapt RaceRD to fix the bugs. And this is where our journey begins. So let's see if we can actually make automated program repair to be part of the standard continuous integration pipeline the same way that RaceRD can be made. So, okay, so and here comes our tool, which actually had quite a number of names. So eventually we settled on the name Hippodrome because it's about races. And this, like the whole idea is how to adapt RaceRD and what it gives to automated program repair. So the key component of RaceRD and other tools such as Pulse and Core Infer that make them scalable is the fact that they work on an interprocedural level by divide and conquer. So they produce summaries. So in the summaries, they are useful for making the analysis scalable because you don't need to reanalyze the same code, but also they capture a rich amount of information about the units of programs, such as functions, such as methods, functions, or classes. Oh, and for us, that was kind of the main enabler. So can we leverage the summaries that are produced in the case of RaceRD to produce the fixes? Okay, so to see what exactly are the summaries that we are dealing with, let's focus for a moment on how exactly RaceRD generates, like what exactly the summaries are and how they help to detect the bugs. Okay, so remember the definition of a data race. So I'm just repeating it. So what RaceRD does, it takes kind of a syntactic over approximation of this notion of the data race. So instead of talking about concurrent accesses as runtime events that happen, RaceRD tries to see if syntactically it can align two pieces of the code in a way that certain syntactic accesses to fields happen without proper synchronization, and at least one of these accesses is a write. So for that, it runs the static analysis that collects the information about this access and then does essentially one-to-one matching. Okay, so how this information is collected by static analysis and how it's represented in the summaries. So remember, this was our working example, a sequential class for the accounts that someone decided to use concurrently and immediately ran into a bunch of problems. So if we try to run get balance and set balance concurrently, we'll see that, first of all, the important part that they both share, they both share the syntactic access path, which is the balance field of this class. So second, when they do that, there is no explicit synchronization. So the reason why, okay, just in case if someone doesn't remember, so the reason why we use synchronization and concurrent programming is to make provide a temporal separation of certain operations in our program. So, okay, concurrency is good if we either have spatial separation or we have temporal separation. So logs give us temporal separation because we know that the critical sections do not overlap. So in this case, there are no logs, hence there is no protection against running at the same time, and accesses from possible from different friends. Okay, there's a typo, and yeah. So how about then the write happens concurrently by set balance. So this is exactly what can manifest the race. Okay, so RaceRD actually produces as summaries for get balance and set balance certain tuples, which capture, in a sense, like what fields are being accessed, what kind of accesses are there, and some additional information that helps to determine whether the conditions for the race are met. And if those conditions, so if we can find two methods of the same class for which these conditions are met, then we are in trouble. Okay, so this is probably the most formal slide of this talk. What exactly the summaries of methods do? So the summaries of the methods are collections of what in RaceRD terminology is called access snapshots. So access snapshot is the 6 tuple, which captures essentially a syntactic information of something, some event happening in the method execution. So it captures the following thing. So the access path that has been affected. So remember, like we could read or write from something, and this is something determined by an access path, usually rooted in this identifier. Then we capture the access type, whether it was a read or write. And this is probably the most controversial decision. So for simplicity and speed, RacerD says, well, we are going to count how many locks is wrapped around this axis. So if this axis happens within a synchronized block, then this component will be at least 1. But if we have synchronized within synchronized, then it's going to be 2. And the reason why, it works actually quite well for the RacerD. It didn't work so well for us, and I'll show why. Okay, so there is also certain contextual information that helps it to work well for certain kinds of applications, such as Android, where there is a dedicated main thread in which everything is synchronized, and classes might come with annotations that they run on this thread. It's actually a very common pattern in UI applications. So, for example, IntelliJ as a Java application, it also has a dedicated UI thread in which everything that needs to be synchronized run, and you can annotate your methods as such. Okay, so then it tracks the fact whether something has been just allocated and hasn't left the scope of the method, so it only exists locally, and this is done by this ownership component. And finally, the piece of information which is not relevant for reporting arrays, but it's very useful for bug reporting, is this path, namely like the class and the methods where exactly the data arrays must be manifested. So now we can imagine how this exactly works in practice. So the RacerD runs a linear analysis that collects summaries, which are the sets of these 6 tuples. And then for each 2 methods of each class, it basically says, okay, so can we have elements in each of the summaries of these 2 methods such that together they this pair can manifest arrays. So this is how arrays is defined. So if we have 2 access snapshots, then if these 2 access snapshots share the same path, and at least one of them is a write, and at least one of them has no locks whatsoever, which is indicated by this L component being 0, and that can happen in any thread, and they talk about non-local objects, then this is arrays. So now let's see how it works with our example. So remember, we had this get balance and set balance. One of them was a read with no locking in any thread, and the object was not freshly allocated, it was a field. And the other one was pretty much all the same things, but the access was a write. So now if we match that against this definition of arrays, yeah, so we've got arrays. Okay, and this is how this access snapshot gives us the useful information. So the problem, okay, so this is obviously arrays. And this is how RacerD detects the risks. Any questions about this aspect? Because this is kind of the important part of the talk. No. So far, so good, right? Okay. Yes, please.
I did have one question. So if you just have, if you just had, say, like a field, instance field, shared field, like X, and that one is just a simple write without a read. So say X equals 0, and then you have another, which is a read. That's not really going to be a race condition, is it? Even though one is.
It is a race condition. You don't know how this simple data type is represented in the memory. So what if it's represented by 2 machine words? And when you write it, it doesn't have to happen atomically. So while you are modifying it, the processor might modify 1 machine word of the representation, and then the read happens, and then it will modify another one. So you see, like, there are very little assumptions on the granularity of those actions that are made. And Java allows you to make this more explicit by declaring such fields volatile, aka atomic, but that's not always the case.
I see. So you're making very few assumptions about the atomic.
Yeah, right. All right, so now we have cleared it up. Let's see what this model is actually not good for. So let's just modify our example a little bit. So you see what changed on the left is that I introduced the new object opt on line 4, and I actually used it for synchronization in the set balance. So and I also added synchronized on line 6 for the get balance. So now we have like 2 synchronized accesses. One is a read, one is a write. Is it a good, like, is this a racer program? Or does it have a race or it doesn't? Who thinks this program has a race? Okay, we have 1 opinion that has a race, 2 opinions. Who thinks this program doesn't have a race? Yeah, the usual situation. Okay, it might or might not have a race. I guess that's the outcome. Okay, this program obviously has a race. So, and the reason is that the synchronization here happens to use different mutual exclusion mutexes, different objects. So, and this is exactly something that the model of RacerD somehow misses, just because guess what? In practice, people very rarely use more than one mutex within one class. No one, like, okay, we didn't run the case study like to measure that explicitly, but that's the reality. So here we artificially constructed an example that managed to make the RacerD to report a false negative. So, and this actually is something that happens very frequently when instead of taking a program which ostensibly has or doesn't have a bug and you try to find the said bugs, you start modifying the programs in an attempt to fix a certain bugs. So these synchronized and synchronized opt might not have been the artifacts that the human has produced, but a repair tool has produced as one of the attempts to fix another problem. And the reason why this is an important situation is that obviously we are going to boldly rely on RacerD's almost soundness to validate the candidates for patches. And if this is a candidate for patch, it needs to be rejected. But with the current implementation of RacerD, the one that is deployed in production, this would not be rejected. And again, this is not a problem for the original intent of using RacerD, but this is a problem for the program repair. Okay, so obviously we had to do something about it, and the fix was surprisingly easy. So we just had to modify one component of the abstract domain, and instead of reporting an integer in the third component, we had to record all syntactic paths for the fields that were used for the objects that were used for synchronization. And indeed, if you think hard, you can also come up with something that uses an aliasing in a non-trivial way that screws this thing up. But this is also something that our repair tool will not introduce. So that's why it was not posing an issue for us. And like my experience with this production grade static analysis tool is that it's always possible to construct a program that violates basic assumptions. But the point is to figure out like whether these are the class of programs that you see very frequently in reality. And most of the time, the class of programs that you see in reality regarding something like concurrency errors is not particularly complicated. Okay, so now this solution just okay. So now we just need to make sure that we have at least one lock in the overlap of these two components for that not to be the race. So, but if these locks are disjoint, as it is the case in our example, then yeah, it is again the race. Okay, so this is actually a meaningful modification that we had to do in the RacerD model, and we actually reran it on the RacerD benchmarks, and we didn't find any new bugs. Okay, so we improved the log domain, and now it looks like that. And now we are on to fixing the problem with programs like that. So let's talk about the repair tools. So that was part about changing RacerD. Now program repair always falls into two components. So first, how to detect the bug, then how to fix the bug. And the reason why you don't see very many papers about program repair at POPL or PLDI, well, occasionally there are papers at UPSLA, is that the part about patch generation is actually pretty difficult to make it formal. So it's most of the time, it's some sort of heuristics that works or some sort of template-based strategy, which doesn't make it less interesting or practical. It's just something that goes slightly against the usual PL agenda of publishing papers. So, okay, so how can we fix in the cheapest possible way, in the way that people will be able to validate? And the reason about this concurrency issue. So we can either introduce more synchronization or we can add volatile annotations. So both of them are viable. So except like if you add only volatile annotations, you go very much by the book of the data race definition, not by the spirit. So you fix the data race definitions because now all the reads and the writes are atomic. So there will be no problems like the one we discussed when I was answering the questions. But if you don't use synchronized block, you have no chance to fix larger atomicity problems. So, and this is something that we didn't target specifically, but it just using synchronization happens to be, using synchronized block happens to be a more versatile solution. And at the end of this talk, I hope we might have some discussion on how this synchronization should be introduced in the more principled or more expressive way. Okay, so now we have this problem, and now we have this culprit. Okay, so where should we introduce the synchronization to fix it? Any suggestions? Yes. one synchronized block around which instruction. And well, you gotta believe it, that's gonna be a perfectly valid solution. So what will happen is that the interprocedural analysis will look up into this candidate, and we'll see that all the accesses that we have to balance, which is where the race happens, they happen through the synchronized block. Okay, so that's clearly an overkill. Any other suggestions of somewhat like more, like, how can we do synchronization more sparingly? So like the reason I'm asking that this is not a very deep technical question, actually pretty much any solution would work here. The point is that I want to show the diversity of solutions for the program repair and why this is actually a problem that is very difficult, the essence of which is very difficult to capture statically. Okay, so one solution is to introduce like one synchronization around this whole thing. So which is fine, and actually that might be a solution that one has in mind, because not only it fixes the data race between access and balance multiple times through set balance and get balance, it also fixes actually much larger domain-specific problem, which is called atomicity violation. So in effect, like the withdrawal should be transactional, so it should behave atomically. And this is something that is very difficult to capture in a general definition of data race, because the atomicity, as many other interesting properties, it's in the eye of the beholder. So like, how would we know that this get balance and set balance, they actually should be executed in a way that there is no interference between them? But this is like where I got bad news, because this is officially above the pay grade of this tool, because usually specifying atomicity, okay, if someone actually can specify the atomicity conditions for that one, they would not have this error probably in the first place. So, and like that's why fixing atomicity violation is difficult, because it usually requires a lot of knowledge that the programmer has. But if the programmer has this knowledge when she writes the code, then there will be no mistake in the first place. So that's why it's a little bit vacuous. Okay, so yeah, so we can have this, and like if we have another method, we can introduce synchronization here, and that also would be nice. So in this particular example, it makes actually more sense to introduce logs at this level. But in many other examples, if we start introducing the logs at like the high level when certain methods are used, we might introduce too much of synchronization overhead, because these methods might not actually enjoy being such coarse-grained, because like okay, so some interleaving would be actually beneficial for the parallelism. So and what we do is we take advantage of this last component of the access snapshots, and we see what exactly is the innermost call in which the data race happens. So you see, like racer_d manifest usually reports the races at like the highest level, because that's when it's easiest to explain to the programmers. And like this set balance here and the get balance here might interfere. But for the sake of fixing, it actually makes sense to go to the source of the race, namely to the library, which somehow exposed the methods that allow someone to introduce the race, and fix them at the source. So like basically we go all the way down to this library, and this is where we introduce synchronization. And again, there are multiple solutions you can apply here. So the simple strategy is just to create a fresh mutex object and wrap, well, in this case, lines 6 and 10 into this object. And you see again, so we might, so the definition of the race is so weak that this is like even not the most basic solution. The most basic solution would be to write to wrap line 6 and the first half of the line 10 and the second half of the line 10 into the synchronization, and that would also work. And this is where we actually start using some common sense and heuristics about how to introduce the patches. Okay, so now imagine that, okay, in some parallel reality where someone actually has written this program, which we have seen before, now we need to fix this. So what do we do? So it turns out that now we have multiple possibilities. So here we can add the synchronized of object into line 7, and that would fix the problem. Hope everyone sees why, because now we have all accesses using the same log, which is this obj, even though it's kind of an overkill because the method 6 uses 2 logs now, both this and obj, or we can add this one here. So yeah, so there are at least these 3 solutions, where the third one is actually create a new object. So what do we do here? So there is a certain heuristics that tries to do what we call the bug clustering. So, okay, I don't suggest you read this definition because they are pretty cryptic. But the idea is essentially we collect all the paths to the methods where certain concurrency bugs occur, and for each of this, for each of the bug, we okay. So basically, we try to take all the data races which happen within the same method and introduce the synchronization at the level of this method with as tight scope as possible. So if we have a number of races that happen in the same method, we will try to wrap them into synchronized blocks. So now how exactly these synchronized blocks are allocated? So we try not to introduce new synchronization objects because that makes the code rather ugly. So instead we try to see what are other objects already used for synchronization and come up with the patches that provide us with an optimal level of synchronization. So here we have three accesses. So the leftmost one is not protected at all, the middle one protected by an object M1, and the right one is protected by an object M2. So what should we do here in order not to multiply the new entities? Okay, arguably not the most elegant solution, but the one which at least is quite principled is that we use the same two logs and we add synchronization for M1 and M2 to the leftmost one, and we also add, actually in this case we don't even need to add, in this case actually the M2 is probably even redundant, so we can just use M1 for all of them. Okay, so and then we perform what's called the log selection. So we look for the most common log that is already used in the cluster. In this case, there is no winner, so so we can just pick M1 or M2 and use it for all accesses. And if there is no such one, we might as well create. If there is no log, then we create it. Okay, so that was patch generation. Actually, there are quite a few more subtleties about that I will cover if the time permits, and I probably should start wrapping up. Okay, so the important part in all the tools for data race repair, and that's usually like a big deal, is that they need to be validated. And they need to be validated for two things, for being safe and for not violating the liveness. Because it's actually very easy to over-synchronize with multiple logs, and then your program is like ridden with deadlocks. And while it's perfectly safe, it's absolutely unusable. So this is where we got lucky and unlucky at the same time, because about the time we were like finishing this work, my ex-colleagues at UCL, James Brotherston, with some collaboration on Facebook, developed the deadlock analysis, the deadlock detection analysis for HRD, which is pretty amazing. So, and we just reused that one with no friction whatsoever, and that is exactly why this paper had like such a hard time being accepted, because most of the components were already there, and the reviewers were just, I mean, okay, so you're going to see evaluation, it's pretty amazing, but this is not something the reviewers appreciated. And the argument was like, we don't care that you managed to beat the state of the art and do better than everyone else, you just didn't work hard enough to get there, because RacerD already gave you most of the tools, you only had to do a little bit of tweaking and figure out how to generate the patches. Okay, so this is like a picture from the paper, essentially what's happening here. So RacerD is responsible for formulating access summaries, detecting the bugs, and once the summaries and the bugs are formulated, another thing that we have done is that instead of spitting out bugs as human reasonable messages, we read them, we spit them out as JSON, which breaks down them to different components. And then Hippodrome is a series of intermediate representations, which first takes the bugs, then makes them into clusters, that compiles them to patch encoding, and then renders this patch encoding as a diff to the AST that needs to be applied to the paper. And then it has two modes. So it either has fully automated mode, in which it applies the series of patches to the program, and then it goes back to the pipeline to make sure that we haven't introduced deadlocks or we haven't missed more bugs, and then it usually converges very fast, like after 2-3 iterations, or it goes into the interactive mode, usually also after this validation, for which we have an IntelliJ plugin, so that allows you just to check whether you like the patch and you want to adopt it. And this is the one that I personally I think has more chances to be used widely, because I would be still scared. Actually, my colleagues have a paper at ICSI this year, whose main discovery is that, like in general, software engineers are very, very skeptical about program repair tools that claim to do everything automatically. That's why I think the interactive mode is slightly more viable as an option. Okay, so yeah, so there are other subtleties about how to do repair and how to produce high quality patches. And here, I guess many of you might have some suggestions, but I unfortunately don't have a formal framework here that would allow to select the best one. I mean, maybe it exists. For example, we can have multiple synchronizations for clustering like this, and we can do some post-processing to merge that. And okay, just by looking at it, it seems like the code on the right is better than the code on the left because it has less contention, so we don't have to acquire and release relog after every iteration. But then who knows? So the code on the right is more coarse-grained. So there is a larger number of things that happen, and maybe the one on the left is desired if we want to have like two loops like this go in an interleaving fashion. Yeah, so another even like more low-level things is like, what if we need to introduce the synchronization block, but it interferes with the declaration and initialization? So like here, for example, on the left, we have two synchronized blocks, which are rather ugly. And on the right, when we merge them together, we need to split the declaration of I and do it before, because it's actually going to be used after the synchronized block on the right, as you can see, the scope. So that's just to preserve the scope. Yeah, so, and finally, just getting back to this example. So if, so now our strategy, default strategy is to fix the bugs essentially at the library level, closer to the source. But if we did what was discussed here, we would also fix atomicity violation, but that was kind of, that would be more accidental, because as I said, fixing atomicity violations without any additional insight is tricky. Okay, so I have like 1 minute of video that I want to show, and this is how it would work in IntelliJ. So you select the file. You see that it's marked at thread safe. So this is one way to indicate to RacerD that this class should be safe to execute from multiple threads. So you run the analysis, and it finds a number of bugs. Okay, so it found a number of bugs. So some suggestions have been introduced, and now what happened? Okay, so there's a bug. Yeah, so you can see the plugin can be improved because there is no highlighting at the level of access. Okay, so now after this, it updated this intention bubbles, and now one of the suggestions, that was very brief, so one of the suggestions here was to adopt one of the changes that was suggested by Hippodrome, and you can see the diff for the change is at the left bottom. So now, again, this was a plugin which was written by an undergrad. It's not very production quality, but in case if you're keen, it's open source and it can be extended. So, okay, so now that has been done in the code itself. Okay, so this is how you can use this tool from IntelliJ. Okay, just a couple of last minutes about how that worked in practice. So we did compare it to the state-of-the-art tools in the concurrency repair, and I have to say that the state-of-the-art is like really not advanced, because the entire community was focusing on 5-line benchmarks. That we managed to do pretty much everything except for the 2 examples and the third one from the bottom. But this is where these tools claim to have fixed atomicity violations in the example similar to one that I have shown, and we did not fix them. So we produced a fix, but that not was for atomicity violations. For everything else, we produced this like fixes which were either the same or better than the state-of-the-art pfix tool. Also, pfix, since it uses a combination of dynamic executions and symbolic runs of Pathfinder, it actually misses bugs, and validating fixes for it takes forever. So you see like hundreds of seconds versus like 1-2 seconds for rerun. Okay, almost there. Okay, yeah, so this is how we are much faster by orders of magnitude, which is what the bottom plot shows. Then we run it on 2 production projects. So this is like a very painful case study to do. So you just browse through commits on GitHub, which have like race or synchronization or something in the message, and you try to find concurrency bugs that real person has fixed and committed. Then you take a snapshot right before it, and you run the tool of it. So on those we have, on those we actually identified 39 bugs. That's in Tomcat and in Google Guava, and that was also fixed by RacerD, and you can look up the paper. The quality of the fixes was either the same, and in a couple of cases better than what humans have done, like, because they like over synchronized where they should have. Okay, almost there. So there are lots of limitations that we don't support, like fine-grained madness, like compare and swap. We don't fix atomicity violation. We could probably do better for log clustering. And finally, and this was like the most unpleasant discovery, the mighty deadlock detector of Racer D can be tricked into detecting no deadlocks if you use anonymous classes and introduce deadlocks right there. All right, so you like create the new thread and you immediately do something within this syntactic new thread definition. That's when it misses deadlocks. That actually costed us one of the submissions. Okay. No, there was like the reviewer was like really diligent, like in coming up with a tool with like a micro example on which Racer D's deadlock detection corrupted spans, and was like very happy to convince everyone that like this is ground projection. Okay, so the paper is available on arXiv. You are welcome to look and do more discussions on how to introduce patches and validate the things. And before I conclude, I would like to keep this discussion on. So solicit new ideas. How can we validate the quality of the fixes? Should we build our static analysis with an idea that someone might use them for repair? I hope we do. And what is the best way to interact with the developer? Should it be automated or dynamic? Okay, so this is kind of the gist. We have the Docker image, the plugin, and this is what I have. So thank you very much. Happy to have a discussion now.
All right. Thank you very much, Ilya. Questions?
So I'm Dan from Imperial College London, and one thing that I would be curious to find out more, can you describe a bit the deadlock detection process? I didn't quite understand how it works.
Well, okay, so the deadlock detection process here is something that we use as a black box, so we didn't develop it.
Okay.
But the way it works, and I'm wondering if there is someone in the gather or in the room who knows more about it, is that it also runs into procedure analysis that collects some sort of summaries, but then it tries to detect the cycles between acquiring the logs, which is which would manifest the deadlock. So there is a paper by James Brotherson, Max Kanovich, and others from Nikos and I guess Paul Brunet from UCL that was published at AZ last year that describes that in detail. We are just the clients of this analysis.
Hi, I'm Luca. So I was curious if I correctly understand the fix is performed at source level. So
Yes.
What do you think about bytecode levels? There are some issues related to apply a fix at bytecode level, or because typically in Java you have many third-party libraries or stuff like that. Then I don't know. It's just
Okay, so
curiosity.
the question is like, okay, the fix, why we don't fix the bytecode, but why we fix the source code. So, okay, I guess this is one of the main kind of assumptions for modus operandi of Racer D and others tools in Infer, that they are not very much concerned with the library code. They are concerned with the code that you are writing and you're about to deploy, and that needs to be validated. So can there be races in the libraries? Sure, they can, but they are not the responsibility of the tool. So the tool analyzes the source code. The analysis works at the level of the source code, and that's why patches are also produced at the level of the source code.
Okay, thank you.
Thanks. I'm Simon. When you switch the summary from using a natural number to the set, the way it seems is you give up the ability to dynamically compute the log. So if the log was behind the getter or so, you can't really write that in the set anymore, right?
Okay, I'm not sure I fully understand the scenario. So if the log was behind the
The
getter, that log will be manifested in the signature of this getter. And if you call this getter from your caller method, then this log will be still present in the signature of that method, but through some qualifier of an object of whose getter you have called.
I was thinking more about when you switch the natural number to the set, you record the paths to the logs in the set, right? It was like this and this dot object and
yes,
things like that. But if your log is dynamically computed because it's hidden behind a getter or something, could you also add that to the set?
Not sure about the getter thing, but if you have dynamic allocated logs, then there is very little you can do. So even the original RacerD, one of the main assumptions which we list in the Rousseau paper is that we work with syntactic, like with lexically scoped blocks that are explicitly manifested. It's not something that you compute on the fly.
Okay. Yeah. Thanks.
Any more questions? We still have a few minutes. I have more of a remark. I like that the fact that this exploits this sort of mines what's in the summary of Infer that's already there, because Infer knows already so much about your code, but what it uses it for is something very limited, which is just reporting a few bugs. But I'm sure and that's a good example of let's look at that data and do something more with it.
I'm pretty sure there's like way more to be mined from the summaries that Infer produces for other analysis. So for data races, the difficult part is actually to create a patch. There was a paper, one of the very few that looks at static analysis in the context of repair by Claire Leguet and Renard Van Tonder at XC, I think like a couple of years before this one, where they fixed memory leaks using the ordinary summary of Infer, like basically just figuring out, okay, what should be the anti-frame for that, for the thing, and then synthesize the allocation statement or read or write statement to satisfy this anti-frame. And that was it worked really well because it was a very local repair procedure, which was following immediately from the separation logic footprint inferred by the analysis. But in this case, well, first of all, like we have lots of freedom where to put the synchronization blocks, and yeah, so that's what makes this repair like slightly less principled and more complicated. Yes.
One question I have is, if given the sort of definition that RacerD uses for what a race condition is there ever a case where it can spit out false positives or?
Okay, so what about false positives, false negatives, and things like that? So what's the impact on the repair? So let me just answer that in bulk. So if your analysis gives false positive, nothing bad happens. You will get a fix that in the worst case scenario will get your programs, like will make your program slightly slower. Yeah. So if you have false negative, well, okay, that's the same thing as for the analysis you missed about. Yeah. Okay, so that's.
Actually, speaking of that, have you measured if the programs you fix are slower as a result?
No, we have not, because it was already enough hell to make this thing compile. And to benchmark that, okay, so like the state of the art is really poor in like design and benchmark. So most of this work was actually assembling the suite from other tools. But like there are like crazy stories. Like I don't know like how that repair community functions. Like pfix like introduced bugs like openly in the most trivial examples that was not acknowledged in the paper. So our things was rejected by the reviewer saying that another tool which will not be mentioned can fix your problem. And from the paper, it looked like the tool is just like openly unsound. But the tool was nowhere to be found on the internet. It was not accessible. It took us half a year to get the binary of that tool from its author. And there was like, we were under pressure that the author is developing this tool as we keep poking him. But once we got them, we just reproduced like exactly what was our claim, that their tool is unsound and ours is. Yeah, so benchmarking is hell on wheels. And I now have a lot of respect to people who do reproduction studies and just publish papers with no technical results, but saying, yeah, so we have reproduced a bunch of things, so they work. Okay, that was a rant.
Okay, I have another question. Maybe you've mentioned this, but how do you generate the source fixes? Is that from inside Infer or outside? Because another thing that's a bit hard to do is like inserting text, modifying program text when you start.
Yeah, so that like there was a certain amount of work put into that binary. I don't quite remember which representation we ended up using, but I think there is this Okamo library for Java ST maintained by someone who now works for that team too. David Pichardie, exactly. Yeah, so we basically just modified the ASTs in this representation and printed them.
Okay, thanks again, Ilya.
Thank you.
Yeah. And now we have a break that ends our session. Thank you. Hello? 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 What's this like? Maybe.
Yes.
Hello? Hello? Okay.
The static seems to be on, so that's good. Just place this in your pocket. Hello?
So is there any indicator of whether we're muted or not? This press to mute?
Yeah. There's a little indicator on the screen there. And so it's just that little
Okay.
indicator there.
Ah, I see.
Yeah.
Mute. Yeah, you can hear. It seems to be working now. Are subtitles available? Ew. Okay. Guess not. Guess it doesn't work. Hello, hello. All right, I assume we're audible.
Yeah, it is streaming.
Okay, so
All right. Our next talk, do we have 3 speakers? Yes. Awesome. It's Matthew Jin, Xin-Chi, and Xiaoyu Li are going to present their work on InfoShop in the past few years. And Matthew has the mic first, I think. So, I know, Shin, let's go. Thank you.
Thank you, Jules. Thank you, everyone, for coming. Before we get started, I just want to say thank you, Ezgi, for inviting us, and also the Infer team, and especially Jules to work with us closely for the past several years to make InferSharp where it's at today. So, my name is Shin Chi, and you will be hearing my colleagues Matthew Jing and Xiao Yu to talk about 4 things today. So first one is what InferSharp accomplished for .NET. The second one is our general learnings from developing a front end for Infer, and also the challenges that we encountered throughout the journey. The third topic is going to be how we productizing Infer for .NET, and there are some key intellectual hello.
You can also use. Does my mic work?
Hello.
Hello.
Okay.
Hello.
I'll just grab it. Hello. 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 Okay. So sorry for the technical difficulty. So for the third point, prototype how we productize Infer for .NET, and we contributed some key intellectual property back to the Infer community, which all of you can leverage in your field. And lastly, how Infer fuels AI for code research at Microsoft. So I'll pass the mic down to Matthew.
Great. So I want to start by talking a bit about what the opportunity that Infer has brought to .NET. So there are 2 main classes that the existing .NET static analysis tools lie in today. There are compiler integrated ones like Roslyn analyzers and Synopsis Seeker. They sort of work within your build system to report warnings. That think the squiggly line when you use the wrong type, or the something like that. There are also signature and pattern-based tools. They find, think FXCOP, which is kind of more of a linter, or CodeQL, which is kind of a query-based approach to trying to find issues or patterns of bugs. But what InferSharp accomplished for .NET is it's really the first scalable and proof-based .NET static analysis. It works interprocedurally to detect issues like nullity references, resource leaks, thread safety violations, with the opportunity to detect a lot more than that too. And this is cool because it works at scale, unlike a lot of other tools that are kind of is deployed at an industry scale, which is one of the unique things about these kinds of technologies. Additionally, our platform supports all of the .NET languages. Think C#, F#, X++, particular latter few may not have support in some of the modern static analysis tools available today. And I want to emphasize that our technology works regardless of the platform you're working on. .NET Framework, .NET Core, Unity, Xamarin. For example, Oculus is built on the Unity platform, and they actually even can use Infer through InferSharp. So I'm going to go over in this talk now some general learnings we had from developing a whole front end for Infer. So one of the first things we ran into when we first approached this project was a language barrier issue. Two main challenges in particular. One, there's no way to parse C# bytecode in OCaml. And another is that as a sort of a new college grad with a bachelor's degree, I never actually learned functional programming. So I was much more familiar with like object-oriented languages. So trying to sort of parse bytecode I'm unfamiliar with in a language that I'm also unfamiliar with, it was a bit of a daunting task. But nonetheless, we started by thinking, hey, what are some potential solutions we can think of? One, well, maybe we could lower the CIL into Java bytecode, use the Java front end written by the Infer team, and maybe that will work. But of course, that poses issues. For example, if I was to map, how do I map the bug localization back into C#? You can imagine that could become a whole nest of issues, especially if you think about there are certain Java things that don't exist in C# and vice versa. How would you handle those? Okay, so that seems not to work too great. What about write a whole CIL parser in OCaml? Because then, and then run the whole translation in OCaml. But again, that sort of not only demands that we write sort of a whole language, like bytecode parser in OCaml, but also I'm still stuck in OCaml, which is kind of hard for me. Okay, so what we ended up doing is we write the whole front end in C#. We leverage an existing .NET CIL parser. It's called mono.cecil. One of the cool things is it's like well tested and written by someone who's very familiar in that kind of space. And we actually serialize we dump all of the SIL we translate it into a JSON file, which I'll get into later, and deserialize it on the camel side to cross over into and make this work for infer. All right, so a bit of an overview of our pipeline. So we actually start from, sorry, that graphic is a bit hard to read, but at the top left there, from the first one, the source is, we start from the .NET-based source code, of course. And then we, of course, that gets translated into the binaries, and we decompile that to get the CIL, the .NET bytecode that underlies them. This is what we translate into the SIL, the small for intermediate language representation that is understood by infer. And that is what we then dump into a JSON file, which can be, we just serialize into JSON and deserialize it using a common OCaml JSON parsing library, so it all kind of works neatly. One of the cool things about this is if you want to go and write a JavaScript front end for infer or a Python front end, you can kind of use this same technology, which confers certain benefits, which I'll get into shortly. All right. So just a bit about how the infer sharp translation works. It's very similar, actually, to what the infer team did for the Java front end. We basically simulate the whole .NET virtual machine. So we iterate through the instructions. We maintain a .NET program stack. And where appropriate, we synthesize the SIL instructions to create the CFG instructions when necessary. For example, if I had a load null, I would have to, which basically means push null onto the program stack in .NET. Well, actually, that doesn't actually need me to create an SIL instruction. So sometimes you need to create one, sometimes you don't. That's sort of part of the translation, which I'll get into a bit more later. The CFG and type environment are both serialized into a JSON format. All right. So just a quick example of what this pipeline will look like in practice. Let's take a very simple Lambda function here. It basically assigns to an instance field either null or an instantiated object, depending on whether the input Boolean is true or false, right? Fairly simple. And just so to get you a picture of what we do, we start with the loadarg.0 you see there. What that does is it pushes this, actually, in this case, because it's an instance method. So it pushes this onto the stack. Second, you do the loadarg.1. That pushes the bool onto the stack. This is on C# side. You have a branch true so that basically pops the top item of the stack, in this case, the Boolean. And if it's true, you go to IL000B, which in this case is the load null, right? So if the Boolean is true, you push null onto the stack, you store that into, you pop the object reference, which is this, and you store it into the instance object field and return. And of course, in the event that in the flip side, when the Boolean is false, of course, the new object is instantiated. That's the new obj command, and that branches to the store field thing. So you basically denotes the storing of the instantiated object into the field and the return. So that's sort of a simpler example, but just to give you a picture of how we simulate and translate a stack-based language into the SIL. All right, but one of the interesting things we learned when it comes to writing a front end is there's actually no sort of correct representation of any given CIL bytecode. In an extreme case, I could say certain things just do not. They do nothing, and depending and that kind of whether that matters or not is sort of only dependent on how much the extent to which that can result in false positives and negatives in infer. And I'll get a bit more, provide a few more examples here. So kind of, at least in practice, I want to say, because there's not a whole lot of we haven't derived too many theoretical groundings to these claims, but okay information loss in our experience has been, for example, with init obj. So this is an instruction that initializes each field of a value type, like a struct, to its default value. So we actually treat the value type as just a regular old object. We kind of essentially instantiate this as a regular object with certain fields. And actually, sort of structs are final, so they can't be sort of mutated. So theoretically, we believe this is kind of fine because the types aren't nullable. So at least, and this is kind of ensured on the C# end. And thus, we kind of don't result in false positives, false negatives in the analysis. I'm sure Jules may wonder whether this is actually true, but just an example of a liberty, one such liberty. Another liberty, there's an instruction called conv. So that one converts integers across bit counts. For example, 64 bits to 32 bits. I mean, you might end up in overflow issues, and none of that is actually captured in our translation of it. We actually pretend this instruction does nothing, which actually I think could actually pose issues for some of infer's analyzers, but not the ones that we support currently. So we kind of pretend it does nothing, and until we run across those issues in those analyzers, we kind of are okay. There have been times where we took liberties that we definitely that are definitely not quite okay. So for example, when we handle references to variables, think like load arg a, the address of an argument, load the address of a variable, and store into an address. So we actually handle those purely on the translation front end. And in practice, most of the time, this has not, and it's meaning that we actually don't represent sort of the address of a reference to a variable actually in the SIL. Now, sometimes, which is quite rarely, this actually can result, and we've observed this, in false positive nullity references because sometimes people basically pass an integer by reference, and then they assign it 0. And then they look at they dereference that variable elsewhere. So that actually can result in some sort of wonky issues. So that's one case where we threw away information that kind of screwed the analysis a bit. Another is so in the past, I since fixed this issue, we also kind of actually discarded the type checking behavior of isInst. Because we're under the reasoning that, hey, like isInst is kind of this runtime thing. And actually, it does a null check. The way it works in C# is the type check is actually followed by a null check on the variable. So which kind of prevents, we thought, in theory, false positive nullity references. In practice, it came to be that actually the type checking behavior of this particular instruction was very key and can result in some very ridiculous nullity references, which we've discovered in practice, which is why we actually went back and properly handled this. But in general, most of what we learned from this sort of writing a front end and trying to make this work in production for a lot of people is that we want to, that something we can do is sort of translate an instruction most of the time. So in particular, this means that we sometimes fail translation for an instruction, given the prior sequence of instructions that sort of lead to it. An example of this is arbitrarily nested exception handling control flow. Maybe you have like a triple nested try catch, all nested in a try finally. It can be a little hairy to make sure that you consistently route all of the different control flows correctly to make sure that you faithfully represented this to infer so that it can do the analysis properly. So we kind of like, this is an example where we're like, okay, so this nested kind of behavior, we kind of will just fail the translation in this case. And actually, despite sort of doing this, we can actually achieve coverage of over 90% of methods on the vast majority of repositories. So in practice, we found it's more important to try to translate sort of confidently and kind of when we're not confident, we just don't translate at all. But I want to now go to some of the real key design decisions that have made this work for us at Microsoft, and which are quite important. So one is that by working at the bytecode level, the good thing is that the compiler guarantees certain invariants on the .NET stack transitional behavior, which helps make sure that we know what to expect when we receive an instruction, what should be on the stack, what should not be on the stack, and moreover, what exactly we're supposed to do with the stack after the instruction. So that's one sort of nice guarantee we get by proceeding from the bytecode. Another is that by translating from the bytecode, not the AST, we make infer sharp robust to future versions of C#. There's a gigantic team at Microsoft that's devoted to working on this language. With every version of which they release every so often, you get new constructs, new ideas, and new operators. Think like even just the notion of a plus equals can mean completely different things depending on the operands. In some cases, a plus equals on an integer, of course, is an increment. Plus equals on a string is a string concatenation. Plus equals on event subscribers and publishers is actually an event subscription, which is very different from either of those. So you can imagine the level of, and this is just one operator alone. So you can really imagine how that complexity really stacks up if you start from the AST. Think also even just null coalescing operators, which are just syntactic sugar around null checks of variables. You have to handle like null coalescing, the double question mark, the null safe dereference operators. It can become quite a hassle. Whereas in the bytecode, these are just branch arguments that checks whether the thing on the top of the stack is null or not. So we really are made it a little easier to manage from an engineering standpoint this way. Another is that we consume compiled binaries instead of being build integrated. And that's been very key for us because particularly at Microsoft, there are tons of different build systems and they're very complex. Think it can take weeks to build Windows. You can imagine how complicated it would be to say, hey, Windows, would you mind trying to integrate infer into your pipeline? Well, yeah, it would be hard. So one of the cool things we did is we're like, OK, just give us the binaries. We'll do the rest. So your build just needs to run successfully, and we'll run the analysis. One of the main benefits of using the JSON layer that I mentioned earlier is actually allows you to, as I mentioned earlier, sort of use the language of your choice to implement the front end. You can use the tools, in our case, the libraries, so mono.cecil. So that was one of the main reasons. So if you wanted to go and implement something in JavaScript or Python for front end in Python or for JavaScript or Python, you kind of can use whatever you want to do that. There are still cons with using this kind of framework, though. So for example, in practice, we've observed ourselves reporting warnings on library binaries, so resource leaks on XUnit, and null dereferences that the user cannot respond to. So they're kind of like, so why are you reporting 300 warnings here? Because there are only 10 on my source code. Well, this is actually something that we mitigated by applying a filtering in practice in VS and VS Code extensions, which I'll get into later. And for incremental analysis, this is one of the difficulties we have. We actually we kind of can't get it directly from the compiler. So there needs to be additional work to sort of make that a smooth and easy thing. I mean, we can use Git today, but another is that the front end also needs to be generated in an incremental way or support an incremental modification. So, and finally, one thing I wanted to mention about how we handle resource leaks is a bit different than how the Infer team did it for Java, for example. There are a huge number of idisposable types in .NET. So what we did was we kind of pre-crawled tens of thousands of idisposable types across all of the different frameworks like .NET Core, .NET Framework, Unity, Xamarin, and we store them in a baseline type environment that we just load at runtime from disk in a few seconds, and sort of that, and that basically that gives Infer what it needs to figure out, oh, okay, now here are all the idisposable types I need to be mindful of during the analysis. But now I wanted to switch to some other key learnings that we've come across, which is how do we productize, like really make something that works for our customers in the .NET community, because it works great has demonstrably worked great for Facebook, but that you can imagine there might be things we might need to adjust to make this work properly for .NET. And one thing is Infer, it works on Linux with no native Windows support for it or for its dependencies. As Boris mentioned earlier, it's actually really hard to do this too. And also it's kind of a CLI tool. And this is a bit of a mismatch because C# developers, many of them work in Windows, right? And also Visual Studio is their IDE of choice. This thing is meant to be the one-stop shop for development. So they're used to having everything in front of them. They're not necessarily really, it's much nicer to have this sort of be integrated into their IDE. So one simple solution would just be, why don't you just put inference dependencies to Windows? We investigated this, it's really hard. So what do we do? Well, this is why we create a Windows native experience without kind of creating a Windows native Infer. And what I mean by this is we leverage a few things that have come up really recently to make this kind of really nice. One is Windows Subsystem for Linux, WSL, has shipped on Windows builds since mid-2020. Custom WSL distributions were released in early 2022, so just this year. Recently they allowed you to basically package your own whole OS together with your binaries and sort of ship that together, which is really nice. So because by doing this with our pipeline, most Windows users can set up the whole thing with just one click. And from a user perspective, it basically looks like, hey, you've brought Infer to Windows. And here's what to demonstrate this, I'll sort of do a quick demo of what our experience looks like today. Okay. Does it share? I think it only is sharing my. Oh, I can't share my screen for some reason. Let me see. Stop sharing. Stop sharing. Let me attempt this. Let's see if that works. It might be because it's plugged into the. Okay. It might be confusion with the plugging. So let me try to go back to the slides. Just to simplify, I figured there might be some issues with like switching, so I'll just. So I was ready for this issue, potential bug. And let me just get back to where I was. Okay, well, so I was going to do this in VS Code, but fortunately, all of this works perfectly well. We've made it work in Visual Studio, and you can imagine pretty much the exact same thing working in VS Code. So it's as simple as we add a button to your tools menu, and boom, you run the analysis with one click. And you can actually sort of, the cool thing is that the warnings show up like any other compiler warnings. So this is what I was trying to show in the demo. You can actually click through the warnings which are displayed there. And one of the nice things is you can see the issues being talked about in the top right window there with localization information. And one of the nice things that this adds is Infer actually has some useful analysis steps that it displays in its experience. And for null pointer dereference, for example, well, this one is thread safety violation, but for null dereference, you can actually click through all the places where it says, hey, this is where the null was assigned, this is where it got returned, and then it got passed to this method and that method. And you can click through all of the locations, which makes it really easy for developers to validate what the warning looks like. So that's one of the main things we found, and that as sort of shown there. One of the nice things we're able to add by making this kind of an IDE experience. And yeah, so this works just the same for VS Code. And yeah, so you can just, it's as easy as you can fix a bug. In this case, it's doing the null safe dereference. And you rerun the analysis, and boom, it's disappeared. All right, now I'll let Xiaoyu talk a bit more about the serve support.
Thank you, Matt. So you may be wondering what's the technology behind this. So this is Serif. It's actually that's called the static analysis result interchange format, aka Serif. It's an industry standard format for the output of static analysis tools. Our team recently contributed the Serif output support to Infer. So with the Serif output now natively supported in Infer, we enable lots of opportunities for. Can you hear me? Okay, good. We enable lots of opportunities for practicing Infer in many different platforms. Like Matthew Jane just demoed with the Serif viewer extension tools and the WSL2, which is a Windows subsystem for Linux help. We recently shipped the InfoSharp as a VS extension as well as a VS Code extension. Now Infer runs on Windows OS inside IDEs. In addition, Serif also provides a better user experience for CI/CD pipelines such as GitHub Action and Azure DevOps. For InfoSharp GitHub Actions, Serif provides a good security scan UIs, like this example shows. It shows all the founded issues with the brief discussions in this security scan UI. Like in this example, here it shows 2 issues found in analyze the repos, 1 non-dereference and 1 resource leak. If we click on any of the reported issues, more details will show, such as the location highlighted in the code, error message, and even the traces, like just right here. And another sweet thing is user now can choose to dismiss an issue if he or she thinks it is either it is a won't fix, or it is a false positive, or it is used in test. So then the dismissed error will be categorized under the closed tag, and it won't show in any future InfoSharp reports unless you choose to dismiss it, and then it will show in issue report again. So to summarize, we are introducing this centralizing static analysis reporting. So Serif helps to extend Infer in VS and VS Code in Windows and Linux systems. And Serif, in addition, Serif also integrates Infer with CI/CD pipelines such as GitHub security and Azure pipelines. And furthermore, we're thinking Serif can enable more opportunities for other languages and Infer practice on more platforms. So next, my colleague Matthew Jing will jump in again. He will introduce our efforts on AI for code research.
Fantastic. So one of the things that I don't think we've talked about too much before is actually we are the data and AI team. So my team actually really works not on static analysis really at all. But we actually are really a team that's about how do we bring the latest and greatest AI tools to fuel code and build great tools for developers. And the funny thing is that one of the main problems in this space is like, how do we generate the great data to learn our models on? And of course, one of the natural solutions we came up with is maybe static analysis can be used as a good baseline to sort of start trying to learn these models, trying to start learn problematic patterns. But of course, that also brought us to the next question, which is, we need a good static analysis tool to make this work. So that's how it brought us to Infer. And I'm going to talk now about two projects in particular that we've sort of been investing in, which sort of use Infer as a baseline. So one is using deep learning models for vulnerability detection and filtering. Our team published a paper at ICSI 2022 this year, which used GPT-C to apply to the local context, preceding bugs reported by Infer to try to see if they can filter false positives. And the author demonstrated that there can be a marked improvement, in fact. We think this is actually based on the bi-abduction, which is kind of, it uses heuristics to try to decide when and when not to report. So we hypothesize that that's why, in particular, there's opportunity for ML to try to reduce some of the false positives in that context. Future work involves using interprocedural context that you might get from an IR that is sort of filtered appropriately to try to improve the model. Because of course, when you're trying to track complex interprocedural issues like nullity references or resource leaks, there's a lot of interprocedural context that might be lost if you just go look at the local context. So that's one project. Another one is ties to something that we sort of had an earlier presentation on, which is how do we generate patches once we've discovered these bugs. One of the key issues in this space is, high quality patch generation data on which to learn deep learning models is actually quite difficult to obtain at scale. I know Facebook has actually worked on GetAfix as well, but one of their luxuries is that they have a whole sort of lit this up at the company and kind of look at the sort of all of the patches Facebook engineers have written in response to Infer. So, but one cool thing that you can utilize static analysis to accomplish is it provides to generate this patch data is that it can identify sort of mutations to code after which warnings are no longer reported. So you can imagine a pipeline where you basically run Infer on successive commits, and you sort of can look at a method to see before and after Infer no longer reports. Now, I want to say there's a caveat here that's why I mentioned that you need to probably filter a bit, because for example, if I just refactor the method, delete the method, you can have this warning disappear, right? So you need to sort of be somewhat deliberate about how you filter it. But at the end of the day, you can also find some legitimate and useful patterns for how people in practice fix bugs reported by Infer this way. And you can do this at scale sort of by just running Infer on a ton of open source repos. So that's one of the nice things about sort of Infer. And of course, also static analysis is really useful because it provides bug type and bug localization data to the model, so it sort of knows exactly where to start generating a fix. But anyway, that wraps it up for now. So thank you again to the Infer team for having us. We'd love to take any questions.
Thanks a lot to all three of you. Are there any questions in the room? Yes.
Okay, so I'm Luca. I have a question about the choose of analyze seal. So I agree with you that is the best way to support new releases of C# and so on. But I have just a curiosity about sources. So when you use the seal code, you lose a lot of syntactic sugar that can be useful, for the final user. So because you can just, for example, in an alarm, just say it's a line number n, okay? But maybe you lose the columns, and when you have huge statements and huge lines, maybe it's not the best fit for the final user. So my question is, have you think to implement something to add the sources information on stuff like that?
Yeah, no, that's a good point. Yeah, so we report purely at the line level, and definitely that's something that makes sense to us. We haven't a lot of our efforts have been centralized so far, not only on trying to make sure the translation is correct as possible, as I mentioned earlier, it can be quite hairy, and also the sort of how do we put this in the hands of users. But yes, you definitely raise a valid issue. We just haven't sort of prioritized that as one of the top things to work on yet.
Yeah, this would have been one of my questions as well. How do you preserve the line number? Especially since probably you're working on optimized CRL code, right? And then you have to, you know?
Yes. So this is a good line of because so we use mono.cecil, which sort of is quite effective in general at sort of figuring out the line number corresponding to instructions. I will say there's a caveat, and people have complained to us. Async tends to generate like the compiler just inline stuff, and nobody actually wrote the code. And actually, Infer will often find, because maybe like people write cancellation token source for their service in an async method, and it gets reported on line 165,999 because in mono.sessel says that is where the thing is. Now, we basically kind of shrug our shoulders and say we get the line numbers from Sessel. Because we kind of that is a very good point, and something we kind of try to mitigate by trying to, for example, adjusting the reporting. One thing is that it's gonna the resource leak warning will be listed on line like 160,000, but the actual we do say things like this resource was allocated on line 30. So to try to mitigate this very valid issue.
Another question would be, you said you can cover more than 90% of methods, but what does it mean? What do you do for the rest of them? You do have to translate to something, right? No,
we do not. Actually, this is exactly what I'm saying. People, sometimes they like to have like quadruply nested try-catch loops, which also have finally, and it goes everywhere. And actually, we spent a lot of time trying to get the routing of the exception just right, because we're very paranoid. What if we forget this edge is supposed to go there, and Infer says, I don't know what's going on, and suddenly our customers are saying, nothing you're doing works. So we do pay careful attention to, and that's what I was saying is we try to we actually, if it's nested, we actually just say we don't know how to translate this, because we really want to bias towards representing things as faithfully as to our knowledge we can. And I mean, next future work would of course be to expand on that. But
But I didn't understand. What do you do if you choose to not translate it? To like no op or?
We just don't include the method in the CFG. So Infer will not report. So it's just that simple. So if foo has, and this occurs whenever we have you can imagine an instruction we cannot.
As if it was never called.
Yes, as if it doesn't exist. And if that method actually gets invoked by some other method, which we can translate, Infer just assumes that it does nothing, right? Yes, I'm pretty sure. So Infer will just be like, if I can't translate C and it's not in the CFG, and C gets called by B, and B actually is in the CFG, what it'll show is when it hits C, that method, it'll basically assume it does nothing, and sort of in practice we haven't seen too many false positives. Sometimes those gaps can result in false positives, but mostly that has been around things that are like specifically for null checks, like is null or empty, or string.is null or white space. When we initially were running by abduction and Pulse, people were like, so this thing is obviously null checked because it says right here, and Infer is saying this is bad. Clearly, you don't know what you're doing. Well, so that's why we have built models for those kinds of cases. There are a ton of other cases where we make said very liberal assumption that the method does nothing, and in practice, actually, it's okay. So.
One more question, or should I yield them? In the end, you seem to have said you want to use the static analysis to bootstrap machine learning then on this data. But if you have very good static analysis, why would you want to use AI for a code? And the other thing is, do you have any hope of that it would learn to be better than what?
Yes. So so this is that is a very good question. So this also ties to some of the sort of the more historical context. Is other tools I have mentioned in this space, like CodeQL. We had Microsoft invested heavily in something called Prefast and Prefix in the past. These were kind of really pattern-based models. And some of the work in that space was like, okay, so it's really expensive for someone to go and figure out how to write this new rule for this static analyzer and then go and test it. and then get yelled at by engineers who are like, this rule sucks and has the high false positive rate. It's expensive to try to find this. Can we use ML to try to sort of realize that sometimes try to compensate for basically the lack of soundness and lack of precision in the analysis? So that's kind of the hope. Now, and that is a good question because yes, ideally, very intelligent static analysis you don't need this anymore. And that's why sort of our team sort of works on both ends. Infer sort of one of the nice things about a tool like CodeQL is, well, if some huge security vulnerability shows up tomorrow, someone can just add the query for that to the database and get a quick fix. It might take a bit more effort to kind of build the right reasoning into Infer to try to get it to work. So there are pros and cons, and so that's why my team is investing in everything in there.
Sounds very good, yeah, and very good presentation. Thanks.
Thanks.
Thanks. On that topic, I'm legally obligated to make the joke that you already do AI for ML for code because you're doing abstract interpretation.
Yes, yes.
Any other questions? Well, thanks for a fantastic talk. We'll have a few minutes before the next talk to set up the speaker and sync with the schedule.
Hello, hello, hello. Hi, can you hear me? Oh, yes.
All right. Well, let's start the last talk of the day and of the workshop with Rishabh, who's going to talk to us about the Lift platform from Sonotype.
Hello, can you hear me? Perfect. Thanks everyone for coming. So today I'm going to be talking about Lift, Sonotype Lift, which is a cloud-native code quality platform developed by Sonotype. In fact, Infer is one of the analyzers which is integrated with Lift, and we provide recommendations to the developer in the PR stage and also in our web console. I'm going to be talking about how Infer is used on Lift, and also be sharing a screenshot of NASA's GitHub repo and NASA open source engineers commenting on Infer findings. And finally, I'll also talk about how easy it is to actually include any other analyzers with Lift, to integrate other analyzers, and sharing an example for that. So let's get started. I'm Rishabh Mishra. I am a product manager at Sonotype. I am the product manager for Lift, of course. I was a software engineer before, and I moved into product management. I think what really inspires me is enabling technology to make a difference and solve customers' problems, as cliched as that might be. So really taking a step back, right? And understanding how software has evolved. Earlier on, there were dedicated testing teams, there were DevOps teams, DevSecOps teams, licensing, legal. But over the years, we've seen more and more of these responsibilities come towards the developer, which is great because the developer has more control, and that means that, and they have more responsibility. But what it also means is that they do not have enough time to do what they do best, which is to write really awesome code, right? And really thinking about that problem, what we aspire to do is we want to automate quality into your development flow so that developers can focus on what they do best, which is innovate. So what is Lift? Lift is a platform for integrating advanced code analysis with software development. So a primary way folks use Lift is by actually looking at its findings and recommendations with each pull request and then acting on it. When we are thinking about this issue, we really took a leaf out of Infer's playbook. My colleague Stephen mentioned that when Infer was introduced in Facebook, it really got a lot of traction when it was integrated into the CI stage and at the PR stage. And it makes sense, right? Because it's a buddy, it's another team member, and it's providing code review and findings and suggestions at the code review stage where it is expected that these recommendations are provided. So we've really seen great feedback, and even from our own products, Sonotype products like Lifecycle, we've seen great feedback coming from all of our customers there. So we aspire to provide good recommendations to the developer here. Also, since the last time my colleague Stephen spoke here, we've introduced a couple of really great new features. One of them being a dependency management. We've really leveraged our 15-year-long expertise in the SCA and dependency management space to highlight new vulnerabilities or possible vulnerabilities in the code base to the developer in the hopes that they are aware of it and they could actually likely update it and make their code more secure. Besides that, we also provide recommendations for code quality structure, right? It was great seeing the talk earlier about recommendations for race issues by Ilya. And we really love that because we want more and more folks to be focused to help developers and to enable them to actually focus on innovation, right? Some of the key focus areas which we really look at when we are thinking through this, historically in this industry, a low signal to noise ratio is a major issue. Some of my colleagues earlier were also talking about that. And this has really eroded the trust that developers have on tools like this, right? So we are trying to sort of gain back some of that trust. And how do we do it? We do it through a couple of ways. One is by analyzing the fixed rates of all code quality recommendations which we make. In other words, we are really looking at all of the open source projects that are out there, and then looking at each and individual recommendation and figuring out whether it's been actioned on or not. How we define fixed rate is in case of a vulnerable dependency, if a developer has upgraded that dependency, in case of a code quality issue, whether they've actually done something to fix it. So we analyze over thousands or tens of thousands of projects and highlight the findings or the recommendations which have been fixed by the most number of people, percentage-wise. And we really, the reason behind this is that we believe that looking at behavior, developer behavior across the board, we would be able to, it's a good proxy for a high signal to noise ratio. At the same time, we recently included a new tool which is called Refactor First, which really analyzes your God classes and prioritizes your technical debt. So that's something which, it's still a work in progress, but I would say we've made great progress so far. Another big problem that we are trying to solve is the last mile problem for software analysis tooling. My colleague, Stephen, he has created a couple of code quality tools which have gotten a lot of traction. And really the problem he mentioned to me was that when a tool author develops a product, they've maybe tested it in a couple of projects internally in a company, and then they put it out there. Now, what happens next? Developers need to actually install it, build it, and then integrate it at some stage of the development workflow, and then really figure out how to action on those recommendations, right? And this is the problem that we are trying to solve, which is the last mile problem, if we could call it that. And we really hope that this makes different kinds of very important tools accessible to the developer, and that's something which we are really interested in. I'll talk about how you could very easily install Lift on any of your repositories. You can go to lift.sonatype.com. It's as easy as 3 or 4 clicks. You click on install Lift for free. You'd be taken to this page. One shout out here is that Lift is free forever for public repositories. So any of you are contributing for open source, do try it out for sure. Then you click on install it for free. You authorize Lift, and then you decide which repositories you want to give Lift access to. That's it. The moment you do that, Lift analyzes, automatically scans. You'd be able to scan any of your repositories and then surface code quality issues or vulnerable dependencies with Lift. There is a web console of Lift, and I want to highlight a couple of things particularly specific to Infer there. And yes, I can share the screen. So this is what we call the master report, which is a list of all of the findings that you'd get, and it is based on a particular repository which was scanned. This is a web console, by the way. So I have filtered. You can see some of the Infer findings, and you can see some of the null dereference findings. This is Apache Maven. That's the open source project which I've used as an example. Just to give you an idea, right? Like you can see the fixed rates here. You could click on show details. It will give you some more context behind what this issue is. Also, one thing I'd like to share is the software bill of materials which we provide with each scan, which is, sorry, that is the dependency tab. But yeah, so you'd get, you'd get this, what we call the SBOM, or the software bill of materials, a list of all of the dependencies and packages that is used within your code base. And it is sorted by Lift score, which I was alluding to about earlier. You'd also have access to build logs, and you can see which tools have actually run in your scan. Yeah, I just kept these just in case that wasn't working, but yeah. So talking a little more about what happens under the hood. So there's 2 primary workflows that we have with Sonatype Lift. One is that at the PR stage, which is what I talked about. It works with developers. It provides recommendations on GitHub, and we look at behavior, developer interaction with Lift very closely there. We collect feedback. We look at the comments. We look at the fix rates. We really get a lot of great data from there. There's another feature which was recently released by Lyft, which is continuous monitoring. Based on your cadence, based on your choices, you can put up certain repos within your project for continuous monitoring. Now, what does that mean? That, say, overnight, so many, most projects use so many other packages. Say overnight, there's a new vulnerability which is surfaced. We proactively will notify you about that vulnerability and nudge you to actually upgrade that or to fix that. And that's something which is really targeted towards, say, open source project maintainers or, say, dev leads or compliance teams in enterprises. And what really happens is that I talked about the extensibility of Lyft and how Infer is integrated with Lyft. That is through a very easy plugin API that we have, which wraps code analysis tools for integration with Lyft. We have 25 tools right now which are built in, including Infer, Error-Prone, Cobra, Static Check. But it's also super easy to integrate with other user-defined tools or any other tool, really. Some more information on the kind of findings or recommendations that we provide with Lyft. One is, say, this CSRF, which is a cross-site remote forgery issue, which is a lightweight security issue, which is essentially that while configuring Spring, this was disabled, which has slight security issues. There's best practice in deep security issues such as cross-site scripting, and of course, reliability and performance issues like resource leaks and null dereferences, which Infer is really good at. So all of this is included within Sonatype Lyft, which is to really show the whole gamut of findings and recommendations that we can provide to the developer. And as promised, this is NASA's GitHub repository, and there's an info finding, then there a null dereference finding, and it has been fixed. So that's something which was really exciting for us when we saw this. And we help projects like this. We are installed in more than 2,000 open source repositories, 40 or 50% of which is Java, actually. So Info was actually the first tool supported by the Lyft platform. It was then called Muse and started by my colleague, Steven. It runs on every Java, C, and C++ project analyzed by Lyft. And it's really unique. It brings its value in really because it provides deep semantic analysis to highlight code quality issues. And that's something we really aspire for. We want to go beyond security. We want to go beyond syntax and actually look at semantic issues as well, which require deep analysis. Looking at some statistics of Infer within Lyft, 14% of Lyft fixed issues in Java code are due to Infer, which is a substantial percentage. 50%, so Infer issues on Java are 50% more likely to be solved, to be fixed, than Infer issues on C and C++. I found this a little interesting, which is the kind of issues which Infer highlights for the projects. 58% of them are null dereference issues, followed by thread safety and resource leak. One nice bit of feedback that we got here was that though not all repositories on GitHub are multi-threaded, one of our customers, when they saw this recommendation, they actually used the word magic. This was magic happening. So those are the kind of feedback that we really look for. So how do you add your tool to Lyft? It's really, really easy if you ask me. So you just go to this site. There's an API, the plugin API, which I talked about, which is used to wrap tools. And then you just have to edit your config file, include this one line there. And then the tool, along with its recommendation, appears in both pull request comments as well as our dashboard, which I'd shown you earlier. And finally, just as an example of a recent feature of another tool, we worked with one of our open source collaborators who was the maintainer at Apache Solar. And we integrated Refactor First, which really looks at your God classes. And for those of you who know, God classes are really heavy and they are often ignored, and they contain a myriad of issues which are not connected with each other, right? this really analyzes the God classes and prioritizes issues which you must fix based on two primary parameters. One is the change proneness, which is we analyze the God classes in the past and we see how often it has been changed, and also the effort which it would require to fix that. So we prioritize the findings based on that, and we really nudge and try to provide as much value, as much signal as opposed to noise when we are interacting with the developer. So summarizing the talk today, we want to automate code quality into your workflow. We provide highly relevant recommendations to developers at the right place and hopefully at the right time. Lyft is extensible and eliminates friction for the developer. And yeah, we really want to help both tool authors and developers to get value out of this. And Infer is, of course, the first tool that we had integrated with. And Lyft goes beyond syntactical and semantic issues by leveraging our expertise in the SCN dependency management space, and really try to be the one tool which any developer can use to better their code and to make the projects of better quality. So that's me. Thanks for your time. I appreciate it. Questions?
Thanks a lot. Any questions? Thank you very much. So a question regarding enabling this on like Java repos. You said you can just add a GitHub app and it will just run, right? But Infer requires like custom build. How do you make sure the build steps succeed if it's because Infer doesn't work on like just the code or syntax itself? You actually have to build the source.
So for Java projects, what we usually do is once somebody's integrated or say authorized Lyft to access their repo, then you'd run the, say on a PR at the PR stage, right? You'd run that and you'd get recommendations based on that particular PR. So there's a diff which is calculated between your existing code and the new code that you've introduced, and only the new code, say the dependencies that you've introduced or the code quality issues which are there in your new code in the diff is what we highlight to the user.
Right, but the diff is, you still need somehow to compile it, right? Otherwise, Infer can't, correct me if I'm Jules, like you cannot like tell this isn't a problem. Let's say you change 2 files. Somehow you need to know how to compile them before, say hey, like here's an issue on this file, for example.
I would be happy to connect with you later. Sure. And get this from my team and let you know how the inner workings of this specific pieces.
Thank you.
No worries.
Hey, this seems like a really cool tool. So when it runs on pull requests, I think you must have some filter, so you only report the issues on new code. Is that right? Only the new code in the pull request? But there may be hundreds or thousands of existing issues that are already there in a code. Do you have a way to help users try to gradually reduce those issues, or even mark some of them as, I'm not going to fix this, and so that they don't have to pay attention to it anymore?
Oh yeah. So the first time you do this analysis, all of your code is analyzed, right? So the first time, that is not at the PR stage, that is in our web console. So you've authorized GitHub, and then you can carry out scans for each of your individual repositories within our Lyft web console. So definitely you can look at all of the issues, the dependencies in your old code as well. But the reason that we highlight new vulnerabilities or new code issues is because the feedback that we've gotten from developers, and this is like across the board, right? Like most developers, they are confused when they are shown old dependencies or old issues. They're like, hey, I didn't introduce this. Why are you showing this to me, right? So that's the problem that we are trying to solve by actually highlighting just the new issues.
Right. Okay. Thank you.
Hi, so I have a question about the architecture. So I don't understand where the analyzer are located. So in cloud, right? So because I'm thinking about customers that maybe don't want to have clouds. I think there are many customers that want just an on-premise solution. There is something about that, or I don't know. Yeah, it's very cool, but yeah, for public repositories, it's cool, but maybe for private or on-premise solution, it's difficult to apply it. I don't know. It's just
yeah. I think that's a very good question. And yes, there is currently Lyft is targeted towards open source projects primarily, right? We are looking at finding product market fit by actually helping many open source projects and talking and collaborating with many influential open source maintainers. Generally, the enterprise customers that we have, and we have a lot of them, they work with our enterprise product. Something, I wouldn't call it an enterprise product, but it's targeted more towards enterprises, which is called Sonatype Lifecycle. So that has an on-prem offering as well. And yes, in the future, even when we are enhancing Lyft and we sort of open it out commercially, we'll definitely look to solve that problem.
Okay, thank you.
No worries.
I don't know.
So at one point you had like vulnerabilities are found and will alert you automatically. I was just curious, like who finds the vulnerabilities? And the reason I ask is because a lot of times the open source community, for the more complicated vulnerabilities, there can be like a debate. Like if you just pull them from like the CVE database, like it may or may not be accurate because maybe the maintainers like debating it's even a vulnerability, or maybe in certain circumstances it's not. So are these like tools or from CVE, or where do they come from?
I'm glad you asked that question. So yes, initially Lyft was using the National Vulnerability Database to look for the CVEs, and we are well aware that there are lots of false positives there, and sometimes they are not even actionable, right? So there is another process within that our data and research team goes through, which is actually enhancing and sort of correcting a lot of this data, right? So Lyft is the only open source tool, if I can say that, which uses a hand-curated database as of now, right? So our research and analysis team actually corrects a lot of the public vulnerabilities, and then this result is reflected within Lyft. We are planning to enhance this even further and even provide remediation advice at some point in the future.
Oh, that's exciting, because it's a pain in the neck, and having multiple teams do this on a large scale is kind of a waste of time.
Yes, we face that problem every single day.
Yeah.
Cool. What kind of processes do you have to sort of pick up the latest info? Because if I understand correctly, those are based on the bioabduction framework. So when do you decide, for example, that you said they should be using Pulse, and how do you go about that? And if Infer accidentally checks in like a bug that is crashing people's code somehow or something, how do you sort of manage these kinds of hairiness that can happen when you deal with these things?
That's a very good question. I would have to talk to my data team about that. Perhaps Jules also knows a little bit of
Awesome. Does anyone else have any questions for Shav? If not, I have one too. One question for you is, you mentioned that in the dashboard, it sorts potential issues by fix rate. And so you can see kind of which issues are potentially most relevant to developers that way. Do you hide any results off of that, or is it only used to kind of sort? Like, is there a thresholding or some kind of heuristic to decide which of those are going to be surfaced, or is it purely just a relevance sorting?
I think that's a very good question, and it ties back to the low signal to noise ratio that plagues this space. We do not filter it out, if you will. So if you say that, hey, I want to see all of the issues, you will see all. But we've made filtering easier, right? So the idea really is, along with fixed rate, and by giving the developer the ability to filter out specific issues that they are looking for. For example, I'd shown issues pertaining to infer in that report, right? We are giving the power to the developers. Though we aspire to reach a stage where we'll be like, okay, these are the 5 issues which you must fix, and then you're good to go, right? And I would say that that problem is not yet solved in the industry. And yeah, I think we should be having that pretty soon.
Awesome, thanks.
All right. Well, thank you very much, Rishabh, for that talk. And that concludes our workshop.
Thank you so much.
Thanks to everyone here. And thanks to our awesome volunteers, Kirby and Nash and Dan and Prashant.